The first thing no one expects is this: the universe might not be growing. It might be fading, not stretching outward, not pushing galaxies farther apart, but slowly, quietly, losing its sharpness, like a painting left too long under cold rain. For more than a century, we repeated a comforting story. Things look redshifted because they're running away from us. Space is expanding, everything is drifting apart, and the cosmos is growing older through endless outward motion. But what if that story is only one way to explain the blur we see? What if galaxies are not fleeing, but dissolving into a cosmic background that is gradually losing the ability to hold them? Imagine watching a distant lighthouse through a fog that thickens with each passing hour. You could believe the lighthouse is moving away. You could believe it is dimming by choice. But maybe the truth is simpler. The fog is eating the clarity itself. Light travels the way it always has. Distance behaves the way it always did. But the fabric carrying that light is losing resolution, as though the grid of reality is thinning thread by thread. And if that is true, then redshift isn't a velocity. It's a symptom, a warning sign that the universe isn't expanding, it's evaporating. The idea sounds impossible at first, even offensive, but impossibility has never stopped the cosmos from behaving exactly as it pleases. Somewhere, in the deep background of reality, something subtle may be happening. The scaffolding of space could be tiring, not stretching thin, but wearing thin. You can imagine the ancient light of distant galaxies passing through that thinning lattice. The points that once held information in place now spaced wider, not because they moved, but because the canvas itself lost threads. And when the canvas frays, even the brightest stroke becomes a blur, hard to accept, even harder to ignore. Because when astronomers look deep enough, the universe does not just look farther, it looks softer, as though everything out there is being held together by a memory that is slowly forgetting itself. You can almost feel it if you close your eyes, something gentle unraveling in the dark. Before we continue, you're listening to Whispers of the Universe. If you're kind enough to leave a small sign, a like, a share, or a quiet subscription, it helps this little corner of stillness stay alive. Thank you. Now breathe and drift with me. Because this first thought, the possibility that the universe is fading, is only the surface of a deeper, stranger notion. What if space does not grow by expanding outward, but by dissolving inward? A universe that expands is simple to picture, points drifting apart, like dots on an inflating balloon. But a universe that dissolves carries a different kind of silence. Not motion, not force, but erosion. The erosion of precision. If space has a smallest scale, a fundamental grain, then perhaps that grain itself is becoming less dense. Not larger, not smaller, just fewer. Like pixels disappearing from a screen while the image tries to hold its shape one last time. Every distance we measure could be embedded in that hidden process. A cosmic lattice that once held matter in place may now be loosening, surrendering the strictness that made geometry possible. A quiet surrender no telescope can see directly, only infer through the softening of everything far away. It's strange to think of the universe as something that can give up, but we are not talking about emotion. We're talking about structure. Structure that could be wearing thin the way an old net loses tension, and the light that travels through it, it stretches not because the lighthouse runs, but because the rope carrying the signal slackens. What if this slackening is the true heartbeat of the cosmos? Scientists already know the vacuum is not empty, it's a restless sea of tiny fluctuations. Space is built from something, and anything built can fatigue. In models where reality has a finite resolution, a discrete underlying texture, the simplest fate is not infinite expansion, it is decay. A slow reduction in the density of points that defines space itself. And when those points thin out, anything crossing them appears redshifted, not because it's fleeing, but because the grid it walks on becomes sparser, spreading out interactions that once occurred with tight regularity. It is the difference between walking across a taut woven carpet and walking across the same carpet after half its threads have been cut. Every step feels longer. Every movement feels stretched, even though nothing in you changed. Now imagine that carpet is the universe. Imagine light is the walker. Imagine galaxies are the patterns embroidered on it. Suddenly, cosmic expansion is not motion, but unraveling. And then you realize a chilling possibility. If the universe is dissolving, then one day far beyond any star, even the idea of distance may lose meaning. But we're not there yet. We start here, at the beginning of a thought that should not exist. A universe whose very fabric loses resolution with time. A universe where information thins, where patterns fade, where the grid of reality becomes sparse like an old photograph dissolving into grain. And somewhere inside that fading field, we live. We walk through a world that pretends to be stable because our senses are too slow to catch the subtle unraveling. Atoms remain atoms. Starlight remains brilliant. But beneath that steadiness is a drift we cannot touch, the drift of the medium carrying everything. Look long enough, far enough, deep enough, and the cosmos looks like a memory-losing detail at the edges. The distant galaxies don't just move away, they blur, not with motion, but with loss. Loss of coherence, loss of precision, loss of the invisible lattice that once held the universe firm. This is the idea that opens our journey, not an expanding cosmos, but a dissolving one. A universe that slowly releases the tension that once bound it. A universe whose highest structures soften into fog. A universe whose farthest lights grow dim, not because they run, but because the path between you and them is losing the discipline needed to carry them. Every telescope ever built has been capturing not distance, but decay. And if this is true, then redshift is not a story of flight, but a whisper of exhaustion. The cosmic background is not a fossil, but the first layer of paint fading from the oldest wall, and the fabric beneath it thins. When you stare deep into the night sky, you are watching the slow softening of a world too vast for us to repair. A world unraveling at a rate so gentle we confuse it for expansion, so quiet we mistake it for motion, so patient we call it natural. But there is nothing natural about fading. Fading is a direction. Fading is a process. Fading is a fate. And the cosmos, calm, cold, beautiful, may be walking toward that fate even now. If you listen closely to the background of existence, you can almost hear the fabric sighing, threads loosening one by one. You can almost imagine the ancient grid beneath reality, slowly losing its sharpness, letting galaxies appear more distant, not because they moved, but because the map beneath them stretched without growing. That thinning, that gentle erosion, is where our story begins. And as the first chapter dissolves, one question rises like a dim star toward the edge of perception. If the universe is fading, where do the first signs appear? The answer lies in the light that left its home billions of years ago and arrives to us now, wearing the fingerprints of a cosmos that may be forgetting how to hold itself together. And this leads us onward into the first signatures of dissolution, waiting in the darkness between galaxies. The first signs never appear where you expect them, not in the bright places, not in the galaxies burning with newborn stars, not in the spirals whose arms whisper across millions of years. They appear in the light that has traveled longest, the light that had the most time to be altered by whatever is happening to the fabric beneath it. When astronomers pointed their instruments toward the deep field, the infinitesimal corner of the sky where countless ancient galaxies hide, they noticed something strange, something that did not quite fit the familiar story. The light coming from those galaxies was not only redshifted, it was softened, as though the fine edges of the spectrum were losing definition, as though photons had been stretched not just in frequency, but in identity. Redshift is supposed to be simple. The farther the source, the longer the wavelength. But the spectra from the most ancient galaxies carried an additional layer, a blur that could not be explained by motion alone. Some called it measurement noise, some called it observational limitations, some dismissed it entirely. But a few wondered, what if the light did not degrade? What if the medium did? Imagine an old road made of cobblestones. A carriage traveling that road once moved smoothly because the stones aligned, fitted, supported each wheel perfectly. But with time, the stones loosen. Gaps form. The wheels jolt, skip, distort. The carriage does not slow down because it grows tired. It slows because the road no longer remembers how to be a road. That is what ancient light might be showing us. Not its own exhaustion, but the exhaustion of space itself. When the James Webb Space Telescope began capturing distant galaxies, whose light had traveled more than 13 billion years, the softness became harder to ignore. Structures that should have been crisp at that distance were not merely faint, they were smudged. And the smudge was consistent, predictable, patterned, a blur with meaning. If the universe were simply expanding, the blur should match the stretch each part of the spectrum pulled with the same gentle proportionality. But what we see is more chaotic, as though certain frequencies struggle more than others, as though the lattice they ride on has become uneven, frayed, inconsistent, not an expanding balloon, more like a thinning membrane. There is an unsettling elegance to the thought. Light was not distorted because it traveled too far, but because space, in its deepest regions, no longer offers a stable corridor for it. Some physicists describe the quantum structure of space as a foam, a restless mesh of fluctuations at unimaginable smallness. But what if even that foam depends on a deeper resolution? What if the foam itself can age? If the quantum grains of space lose density over cosmic time, then light from the early universe would pass through less and less structure, like a painter's brush gliding over a canvas with missing threads. The result? A spectrum that loses detail the way a voice loses clarity inside a collapsing cave. Think about distant quasars beacons, brighter than entire galaxies, powered by supermassive black holes. Their light is so intense, it should carve through the void with razor precision. But even these titanic signals arrive with hairline distortions that do not cleanly align with expansion models. Their structure looks disrupted, not from motion, but from medium fatigue. The first signature of dissolution is not darkness, it is not silence, it is not cold, it is softness. The softening of things that should be sharp. To understand how subtle this is, imagine you were handed two ancient photographs, one printed yesterday, one printed a century ago. Even if both were restored with the same care, the older print would still seem slightly less crisp, its granularity betrayed by time, not because the image changed, but because the material holding it did. The universe may be showing us the same thing on a cosmic scale. Astronomers once thought that distant galaxies looked faint simply because they were far. But faintness has texture, faintness has shape, and the shape we see resembles dissolution more than distance. A dissolving universe would dim galaxies not by pushing them away, but by loosening the field that holds their light. The thinning of spacetime would act like a mist without moisture, a veil without particles, a dilation without movement, a type of cosmic anemia, not a lack of energy, but a lack of structure to carry it. There's another clue, hidden in one of the universe's oldest signals, the cosmic microwave background, the faint afterglow of the earliest moments. Its temperature variations are astonishingly smooth, almost too smooth, as though the fluctuations were blurred by something more than distance and time. This could be the fingerprint of a medium losing its grip. The earliest light did not travel through a perfectly consistent structure. It traveled through a fabric that, even then, may have been thinning in places, unraveling like a tapestry whose threads tired before the story was finished. If dissolution began early, the cosmic background would show hints of it, slight directional inconsistencies, patches where the statistical roughness is gentler than predicted. And indeed, telescopes have found anomalies, small regions where the universe seems too smooth, too uniform, too erased. Cosmologists struggle to explain them. They call them cold spots, anomalous alignments, unexpected symmetries, but all share one trait: a subtle lack of definition. A dissolving fabric would produce exactly that. It's important to consider how counterintuitive this idea is. We expect the universe to thin at the edges, not the center. But dissolution does not need a direction. It does not radiate outward. It creeps through the underlying resolution itself everywhere, quietly, uniformly, the way a sheet of ice melts evenly across a pond before the first hole appears. And yet, the edges show it first. Not because the edges dissolve faster, but because the ancient light from those edges has traveled longest through the thinning grid. Imagine a violin playing a perfect note in a room whose air is gradually removed. The note begins pure, but as the air thins, the note changes, not because the violin changes, but because the medium loses the richness needed to carry the sound. That is how ancient starlight behaves if space loses resolution. Galaxies do not age into smudges. The space between us and them dissolves into one. The first signatures are also found in gravitational lensing, the bending of light by massive objects. Not the strength of the lensing, but the texture of it. In a fully stable space-time fabric, the distortion patterns are crisp, obeying exact mathematical symmetry. But the deepest lensing observations reveal small deviations, not noise, but systematic quirks, as though the lens is being projected onto a screen that has lost some pixels. A dissolving universe would create precisely such a phenomenon, lensing that is accurate in shape, but soft in resolution. Even the clustering of galaxies shows hints. Instead of forming sharp filamentary structures everywhere, there are regions where the filaments look washed out, as though the web of matter that should be strong has been thinned by an invisible erosion. When cosmologists map these regions, they often blame dark energy or statistical error. But what if those regions are scars, places where the lattice has lost more resolution than its surroundings? A universe that expands would stretch the web. A universe that dissolves would blur it, and the blur is what we see. There is a paradox hiding in all this. If space is dissolving, why do nearby galaxies look crisp? Why don't we observe the blurring locally? The answer may be as simple as duration. Nearby galaxies are close not just in distance, but in light time. Their light has passed through far less thinning fabric. Their photons have not endured the long erosion that ancient light endured. We see the universe through a time machine, and the farther back we look, the deeper we peer into the medium's exhaustion. The first signatures of dissolution are not found in our neighborhood, but in the oldest light, the faintest echoes, the most delicate patterns. The universe hides its unraveling in the distance, confident that we will blame motion instead of decay. We once imagined cosmic redshift as the stretching of an expanding stage. But what if the stage itself is weakening? What if distances seem longer because the very notion of distance is losing its strictness? A dissolving universe would mimic expansion perfectly. Every measure we make would tell the same story, but for a completely different reason. In an expanding universe, galaxies separate because space grows. In a dissolving universe, galaxies separate because the points that anchor distance are vanishing. Space does not grow. Space loses definition, and things drift apart like dots on a sheet whose fibers have thinned. As the fabric wears down, everything appears more distant, not because it moved, but because the ruler itself stretched without expanding. This distinction is subtle, almost invisible, and yet it changes everything. If expansion is motion, the universe has an outward direction, but if dissolution is erosion, the universe has an inward truth, a truth that leads us deeper into the next thought. If dissolution begins with information, what exactly is the universe losing first? Why does light blur in specific ways? Why do some regions soften more than others? Why does the early universe look too smooth, as though someone smeared a finger across the first canvas of reality? The answers lie in the most fragile thing the cosmos carries, the one element that binds everything into form: information. And if information itself begins to fade, then matter, energy, and even meaning will follow. This is where the next step begins in the quiet erosion of the universe's most fundamental language, the language that holds everything together and may now be whispering itself away. The universe does not dissolve by tearing itself apart. It dissolves by losing the very thing that once held it together: information. Not data in the human sense, not the kind stored on disks, servers, or memories, but the deeper kind, the kind woven into the quantum fields that define the identity of everything. Information that tells a particle how to be itself. Information that instructs spacetime how to curve. Information that allows energy to exchange from one place to another without losing coherence. Without that primordial information, nothing holds its form, nothing remembers its behavior, nothing knows its boundaries. And somewhere in the ancient universe, that memory began to thin. It starts subtly, too subtly for instruments to notice directly. Patterns in the cosmic microwave background appear smoother than expected, not because the early universe was uniform, but because the record of its roughness has faded over time. Dissolution begins, the same way paper ages, not with a tear, but with a softening of the fibers. Physicists talk about information conservation as an axiom so rigid that violating it seems impossible. Yet the cosmos rarely respects the axioms we write for it. Information conservation works beautifully when the underlying medium is stable, when the grid of spacetime holds every imprint with unwavering resolution. But what happens when that grid itself begins to blur? The deepest theories, those that describe spacetime as emergent, not fundamental, suggest that information is encoded in the tiniest steps of the cosmic lattice. Each point in space is not a dot, but a storage unit, a location that knows something about curvature, matter, or energy. If the density of those units decreases, then the universe loses its capacity to remember. This is the beginning of cosmic fading, not chaos, not destruction, a gentle thinning of the memory of reality. Information does not disappear, it becomes diluted. Think of it like ink in water. The ink does not vanish, but the pattern loses sharpness. Edges soften, colors blur. Eventually, what was once a detailed image becomes only a faint shadow of itself. Light, from the earliest galaxies, shows this effect. Not just redshifted, but desaturated, as though the information that once described its complexity has been stretched too far over an eroding medium. If information is the true fabric of the cosmos, the universe may not expand or contract, it may simply lose bits of its internal script with time. Somewhere at the intersection of quantum theory and gravitational geometry lies a quiet truth. The universe is not made of things, it is made of instructions that tell things what to be. And the instructions are weakening. To see how deep this goes, imagine a single hydrogen atom, the simplest atom in existence. It is defined entirely by information. The strength of the electric field, the mass of the proton, the charge of the electron, the curvature of the local space-time that contains it. Every parameter is a piece of information encoded in the cosmic field. If the underlying resolution weakens, those parameters fluctuate more easily. Not dangerously, just softly. Barely enough for any experiment to catch, unless that atom's light travels across billions of years through a dissolving universe. And that is the light we observe. The light that carries not only its own story, but the slowly fading memory of the cosmos itself. This is why the oldest photons look blurred. They were painted across a canvas whose texture changed as they moved. Consider the idea of decoherence, the process by which quantum systems lose their delicate superposition when exposed to their environment. Decoherence is often treated as a local effect, happening only when particles interact with something nearby. But what if the universe itself decoheres? Not locally, but globally. The cosmic environment, the background grid of spacetime, might lose coherence slowly as its resolution fades. A dissolve not of things, but of the rules that stabilize things. Particles would not suddenly flicker or fall apart. They would simply carry weaker informational signatures, like characters in a story whose ink has faded with centuries. This weakening would be imperceptible at small scales, but unmistakable over cosmic distances. And that is exactly what we see. The oldest signals in the universe look like copies of copies, as if their original instructions have been stretched too thin across an eroding lattice. The puzzle becomes more profound when we examine gravitational waves, ripples in the fabric of spacetime. If the universe were dissolving, these waves should lose sharpness over long distances, not because energy dissipates, but because the medium loses its ability to store curvature with the same precision. Early models show hints of this. A softening of high-frequency structure in distant gravitational wave data. Not enough to claim anything, just enough to whisper. Whispers can be ignored. Patterns cannot. Patterns appear when we look at how information behaves near the cosmic horizon, the farthest edge of what we can observe. There, we find a strange quietness, less variation, less structure, less statistical richness than expected. A smoothing that should not be there, as though the oldest regions of the universe are not simply distant, they are fading into informational silence. Consider what happens when a sound travels across a vast desert. The dunes are not a vacuum. They absorb certain frequencies, damping them. The sound that reaches you is softer, emptier, not because the source changed, but because the medium removed information selectively. The universe may be doing the same thing to the oldest light, not absorbing energy, but erasing detail. A cosmic low-pass filter, not because it was designed, but because its structure is weakening with time. There is a deeper, more unsettling implication. If information fades, then entropy, the measure of disorder, may not be rising as we think. Perhaps the universe is not increasing in disorder. Perhaps it is losing the resolution required to define disorder at all. Entropy might not be climbing upward. The staircase itself may be dissolving, but the most profound consequence hides inside a single question. What disappears first when information fades? Not particles, not forces, not energy. The first thing to dissolve is precision. Precision is what makes a particle distinct from another. It is what allows gravity to follow exact curves. It is what gives light its color, its frequency, its fingerprint. It is what gives distances their meaning. Lose precision, and the universe becomes a watercolor. Boundaries blur, identities blend, structures soften. This is likely the earliest stage of cosmic dissolution. The universe has not lost matter. It has lost clarity, and clarity may be more important than we ever understood. The ancient cosmos is often described as primordial, but perhaps we misread its simplicity. Perhaps it was not simple, perhaps it was sharp, intricate, high resolution. And the blur we observe today is not a portrait of its youth, but the erosion of its memory. Every pattern we see in the cosmic microwave background might once have been finer, richer, more detailed, but time, distance, and the thinning lattice have worn them down. Information does not vanish abruptly. It fades symmetrically, like breath leaving glass. If dissolution is real, then what we call cosmic expansion may be nothing more than the stretching of information across a weakening grid, a misinterpretation born from the assumption that space is stable. But space is not stable. Space is a field, and fields age. When a field loses resolution, it does not collapse. It drifts, it softens, it forgets. And in that forgetting, everything built upon it begins to blur. The oldest quasars are not dim because they are far. They are dim Because their signatures have been smeared thin across a dissolving cosmos. Even dark matter distributions show hints of smoothing that do not align with standard models, not because dark matter behaves strangely, but because the structure holding it is changing. The universe hides its fade beneath the appearance of expansion, the way a shadow stretches, not because the object moves, but because the light behind it weakens. The first true sign of dissolution is not catastrophe. It is not collapse. It is not the death of stars or the silence of galaxies. It is the softening of everything ancient. And from that softening emerges a deeper question. If information fades at the edges of time, does the resolution of space itself depend on age? Is reality sharper when it is young? Is the present crisper than the past? Does time dilute information the way distance dilutes light? This is not just a theoretical curiosity. If true, it changes the nature of cosmology. The universe would not be a uniform system evolving symmetrically. It would be a memory field, growing weaker with age. A cosmos that remembers less of itself as it grows older. A cosmos drifting toward a state where information density approaches zero. Not a void, not a collapse, but a return to an almost featureless potential. And if that is where we are headed, then the question becomes, what does space look like when resolution is lost? What does the universe become when the last threads thin? When the lattice forgets how to store curvature, mass, light, distance? That question leads us into the next step. If information is fading, then the very structure of space, the resolution of the grid, must follow. And that brings us to the next chapter of this quiet unraveling. What happens when the resolution of space itself begins to dissolve? If information is the first thing to fade, then space, the stage that holds everything, must eventually feel the thinning. Not through tearing, not through rupture, through a much quieter process, the loss of resolution. We often imagine space as smooth, continuous, infinitely divisible, but the theories that reach deepest beneath quantum fields whisper something else. That space is granular, pixelated, a vast lattice of minuscule units whose density defines the precision of reality. This lattice, invisible and silent, is the framework on which distances exist, on which angles hold, on which motion becomes meaningful. Without resolution, space is not space. It is a blank potential without structure. And deep in the ancient cosmos, the regions whose light has traveled longest, the resolution appears lower, the fabric softer, as though the cosmic grid has fewer threads than it once had. Physicists call the smallest possible spacing the Planck length, a scale beyond which measurement loses meaning. Some imagine these lengths are fixed forever, but nothing in the universe has ever truly been fixed. Not stars, not elements, not constants, not even vacuum. If the density of these fundamental units decreases, space does not expand. Space becomes coarser. Distances stretch not because they widen, but because the ruler that defines them loses marks. Imagine a measuring tape whose tiny lines slowly fade. The length it measures appears to grow not because anything moved, but because the resolution collapsed. Light traveling through such a medium does not simply redshift, it smears. The smear is subtle, but it grows with distance, accumulating with every billion years traveled. Ancient photons arrive not only stretched in wavelength, but dragged across a thinning grid, each step they take forced to land on a coarser map. You can imagine it like a dancer crossing a floor that once had fine grooves to guide every step, but with time, the grooves fade, the markings blur, and the dancer must improvise between indistinct positions. The universe may be improvising now. The cosmic web, the grand structure of galaxies and filaments, also hints at this thinning. In high-resolution simulations, the cosmic lattice forms delicate, sharp threads and nodes. But real observations show regions where these threads blur, not as though matter scattered, but as though the grid mapping their positions grew uneven. A dissolving resolution makes the universe look smoother, less structured, more soft-spoken at its edges. Even curvature, the core of gravity, depends on resolution. Einstein described gravity as the bending of spacetime, but bending can only be defined if the fabric has a fine enough texture to hold its shape. A coarse net cannot form precise curves. A thinning lattice cannot encode tight gravitational fields. So when resolution fades, gravity does not weaken dramatically, but its precision weakens. Curves that once were sharp become gentle. Lensing that once formed crisp arcs becomes diffused. Not weaker gravity, but blurrier gravity. This blur matches what the deepest lensing observations sometimes show. Patterns too soft, edges too smooth, as though gravity itself passed through a low-resolution medium. The greatest misconception in cosmology may be this: that increasing distance implies expansion, but coarsening resolution produces nearly identical observational signatures. Imagine an image stretched across a canvas. If the canvas loses half its threads, the picture appears larger, not because it grew, but because its details were forced to smear into the remaining fibers. The universe could be doing exactly that. Space may not be expanding the grid beneath. Space may be thinning, pushing details outward because fewer points exist to hold them. A galaxy billions of light years away looks smeared, wider, more red-shifted, because its light must spread across a coarse, dissolving network. This is indistinguishable from expansion unless you look deeply at the texture, and telescopes are only beginning to see that texture. High-energy photons appear to interact differently with distant space-time than low-energy photons. In an expanding universe, all wavelengths should stretch proportionally. But in a dissolving universe, shorter wavelengths lose their sharpness first because fine details require fine resolution. Long wavelengths travel easily across coarse grids. Short wavelengths stutter, scatter, soften. This is the signature we observe in ancient gamma-ray bursts, a softening of high-frequency detail inconsistent with pure expansion, not noise, not error, but the whisper of a dissolving field. Some theorists describe space-time as a tapestry of microloops, each loop carrying the tiniest quantum of area. If the loop's thin, if fewer loops exist in a region, then that region becomes less capable of encoding curvature or information. Distances become less meaningful, trajectories become less precise, light paths become less consistent. A dissolving resolution is not destruction, it is unremembering. Reality forgets how to be sharp, and with each forgotten detail, space grows softer. You can imagine this process spreading across the universe not as flame or fracture, but as a gentle dimming of clarity, a slow quieting of the grid, a subtle evening of structure, not entropy increasing, but definition decreasing. There is a story told in mathematics about fractals, infinite patterns that retain their structure no matter how deep you zoom. Space may once have behaved like such a fractal, intricate at every scale, precise at every depth, but dissolution means the universe is losing its fractal fidelity. Zoom deep enough, and you may find fewer layers than expected, less detail, less resolution, as though the universe is becoming a rough sketch of its former self. There is another subtle clue. Cosmic voids vast, empty regions between galactic clusters. Void mapping shows that these regions appear smoother than models predict, too smooth, as though the grid beneath them has already thinned more than surrounding areas. The edges of the cosmic web look like torn paper, details missing, threads thin, structure light as breath. If dissolution is real, the voids would be the first places where resolution breaks down, not because they are empty, but because emptiness offers no resistance to thinning. Matter slows dissolution by anchoring curvature. Voids offer no anchors, so they fade first. What we see as emptiness might actually be early erasure. Even the behavior of neutrinos, particles that barely interact, supports this idea. Their oscillations behave slightly differently across vast distances than predicted. A dissolving lattice would affect them more than anything else. Not because they interact strongly, but because they travel almost unhindered, sampling the true structure of space-time with unmatched sensitivity. The small irregularities in oscillation frequencies over cosmic baselines may be telling us the grid beneath you is thinning, the resolution of space is changing. But the deepest implication is this: if the universe is losing resolution, then the concept of a constant becomes a fiction of proximity. Constants are only constant locally within regions of stable resolution. Over cosmic scales, the constants may drift, subtly, quietly, not enough to rewrite atoms, just enough to soften the distant universe. And this raises a question no cosmology can ignore. Does resolution fade uniformly? Or does it drift from region to region like a slow tide of erosion? Pictures from the deep fields show galaxies at the same redshift with different degrees of softness, not because of dust, not because of instrument error, but because some lines of sight carry light through regions of space-time that have thinned more than others. A dissolving universe is not a smooth universe. It is a universe eroding in patches, like frost melting unevenly from a cold window. Yet the erosion is gentle, so gentle that life here feels no shift. Atoms vibrate with familiar frequencies, gravity curves with familiar strength, and the Earth spins without a tremor. Local resolution remains high for now. But ancient light reminds us of what lies ahead: the slow softening of the cosmic grid, the gradual thinning of structure, the quiet erasure of precision. And if space is losing its resolution, then what rests upon it must follow. Gravity, matter, motion, identity. The lattice that defines reality is becoming coarse, and everything woven into it will feel the blur, which leads to the next whisper of this unraveling. If the resolution of space dissolves, what happens to the force that depends on that resolution, most gravity? The next chapter steps into that question, following the dimming threads into the quiet fatigue of the universe's oldest force. If space is losing its resolution, then gravity, the curvature of that space, cannot escape the thinning. Curvature requires texture. A sharp bend needs a fine grid to hold the angle. A soft bend can survive on a coarse lattice. But when the grid begins to dissolve, even curvature grows uncertain, like handwriting on paper whose fibers have worn thin. Gravity is often mistaken for a force, but it is not force, it is geometry. The geometry that tells matter how to move. The geometry that instructs light on how to arc through the darkness. The geometry that binds galaxies, shapes stars, hugs planets into orbits. But geometry cannot exist without resolution. A curve is only a curve if the medium beneath it can support its detail. Lose that detail, and the curve blurs. This is the quiet exhaustion that gravity may already be feeling. Not a weakening in strength, but a weakening in precision. A subtle softening of curvature across cosmic distances. The same softening that blurs ancient light may be blurring the gravity that shaped it. We see the hints in the way galaxies rotate. For decades, astrophysicists blamed dark matter for their strange motions. They expected stars in the outskirts to drift slower. Instead, they spin with stubborn velocity, as if some invisible mass binds them. Maybe that is true. Maybe dark matter is the missing ingredient. But there is another possibility. The curvature itself is softening. A dissolving lattice would cause gravity to spread differently, its influence leaking across a coarser grid rather than focusing along fine-resolution pathways. Imagine drawing a perfectly curved arc on crisp parchment. Every detail holds. The ink flows clean. The shape remains loyal to your intent. Now draw the same arc on paper, soaked with humidity, its fibers swollen and weakened. The ink bleeds. The curve becomes less precise, its edges feathered, its form blurred. Gravity drawn on a dissolving universe might behave this way, still present, still guiding motion, but softened. Its instructions less crisp. The strange motions of galaxies could reflect not an excess of unseen matter, but a fatigue in the fabric that encodes their curvature. Consider gravitational lensing, the bending of light around massive objects. It, too, carries a signature that does not entirely fit the standard model. Some lensing arcs appear unnaturally smooth, as though their sharp geometry had been draped across a coarse field. Lensing patterns lose their crispness with distance, not randomly, but proportionally. The farther the signal travels, the more the lattice beneath it seems to diffuse the curvature. A dissolving universe would produce exactly this effect. A tired geometry projected through a tired grid creates an image softened twice. We sometimes describe spacetime as elastic, capable of stretching, warping, rippling. But elasticity requires structural integrity. Stretch a pristine fabric, and it flexes cleanly. Stretch a fabric whose fibers are frayed, and the deformation distributes unevenly. Its shape warped not by force, but by frailty. Gravity in a dissolving universe becomes such a deformation, a curvature that interacts with a weakening texture, a geometry forced to compromise with a medium losing its crispness. The deepest clue may lie in gravitational waves, ripples emitted by the collision of black holes or neutron stars. These waves traverse the cosmos, carrying with them a memory of the violence that created them. But memory requires resolution. If space-time thins as waves pass through it, the waves should lose high-frequency detail, their once sharp ripples stretched into softer forms. Observations show hints of this. Gravitational waves arriving with slight discrepancies in amplitude and detail, especially when their origins lie far across the cosmic web. Not enough to announce new physics, but enough to whisper, once again, that the medium is tired. A tired fabric cannot hold crisp vibration. It muffles, it smears. It lets the sharpest peaks flatten slowly into gentle undulations. But fatigue does not mean collapse. Dissolution is not destruction. The universe does not shatter when its resolution fades, it softens. And the softening spreads in patterns that match the distribution of matter. Regions with dense matter resist dissolution longer because curvature anchors resolution. Gravity pulls threads tighter, holding the lattice more firmly in place. Voids, however vast, open regions between galaxy clusters, offer no such anchor. They dissolve faster, their resolution fading like fog thinning in the morning sun. This disparity creates uneven gravity across immense distances, not weak or strong, just unevenly crisp. Gravity's handwriting grows blurred in the voids, while remaining clearer in dense clusters. This would create slight anomalies in the way galaxies move between voids and filaments. It is exactly what surveys observe: peculiar flows, unexpected drift patterns, motions that seem to obey a hidden map, a map of resolution, not mass. But the most elegant consequence is this: gravity becomes scale-dependent in a dissolving universe. At small scales, solar systems, planets, atoms, resolution remains high. Gravity behaves as precisely as ever. At cosmic scales, superclusters, deep voids, resolution fades. Gravity becomes slightly coarse. This duality explains the consistency of local physics and the oddities of cosmic motion without introducing exotic forces or speculative matter. The universe behaves differently at different scales because its canvas holds different densities of thread. Close to home, the fabric is taut. Far away, the fabric is thin. This thinning is not sudden. It is a slow surrender of cosmic precision, a gradual loosening of the grid, a fatigue that mirrors the age of the universe itself. Gravity's tiredness is not weakness, it is blur, a blur that grows with distance, a blur that matches the softening of ancient starlight, a blur that connects the anomalies of rotation, lensing, structure, and wave. If gravity depends on resolution, then matter depends on gravity, and thus matter itself must eventually feel the thinning. Stars may hold their shapes, planets may cling to their orbits, atoms may dance with the same rhythms, but across the cosmic expanse, the very idea of a stable structure becomes fragile. A galaxy far away looks less like a crisp spiral and more like a memory of a spiral, as though the universe remembers its form but not its detail. This is the deeper implication. Matter, like gravity, may be defined by the resolution at which it is encoded. If that resolution declines, matter does not collapse. It simply becomes less precise, less densely specified, more easily dissolved. Galactic halos may appear more diffuse not because of dark matter, but because the lattice holding their structure no longer has the fidelity needed to define them sharply. The cosmic skeleton becomes looser, the cosmic map becomes gentler, the cosmic boundaries become faint. Gravity is the first to whisper this truth. Matter will be the second. We stand now at the threshold of that next whisper, the unraveling of the physical world as the resolution that defines it gradually dissolves. For if gravity is the bending of a fabric that is losing its texture, then matter must be the stitching that loosens next, which leads quietly into the next unfolding. If gravity is growing tired, how does matter begin to dissolve along with it? The next chapter moves into that slow unraveling, the soft erosion of coherence and mass as the universe continues its long, patient fade. If gravity is the curvature drawn on a fabric losing its resolution, then matter, which relies on that curvature to define itself, must eventually feel the thinning as well. Not suddenly, not catastrophically. Matter dissolves the way old ink dissolves in a book left too long in the rain. Edges soften first, contours blur, identity loosens, grain by grain. To see how matter begins to dissolve, we must start smaller than atoms, smaller than quarks, at the level of the fields that write the script for existence. Every particle you know is not a thing, but a note played by a field. The electron is a vibration of the electron field. The quark is a vibration of the quark field. Even mass, the property that lets matter resist acceleration, is not inherent. It is given by a field, the Higgs field, a silent ocean that endows particles with the drag we call matter. But vibration requires structure. A string cannot make sound if it is dipped in water. A drum cannot echo if its skin is slack. A field cannot define a particle if the lattice encoding its oscillations begins to thin. And thinning is exactly what dissolution brings. Matter begins to dissolve when its fields lose resolution, when the grid on which they vibrate becomes coarse, when the instructions that define them grow faint. This dissolving process does not destroy particles. It makes them less coherent. Coherence is the harmony of a field with itself, how well it remembers its own oscillation, how tightly it holds its identity. When coherence fades, particles do not explode or vanish. They blur in their behavior, subtly shifting the parameters that once defined them with quantum precision. An electron becomes the same electron, but its oscillation may drift in a medium whose resolution is thinning. Not enough to rewrite atoms nearby, but enough to carve faint signatures into the ancient light that carries their patterns across the dissolving cosmos. This is why distant matter looks softer. Its constituent vibrations traveled through a grid, slowly losing the ability to preserve their fidelity. The universe is not destroying matter. It is lowering the bitrate of reality. Think of a high-resolution image compressed into a lower-resolution file. The shapes remain, the objects remain, but the details blur, edges pixelate, fine lines vanish. The identity of the image persists, only softer, less exact. Matter is undergoing a similar fate. Its essential identity persists, but its precision, the fine lines of its quantum script, is fading at the edges of cosmic time. This fading script changes more than the particles themselves. It changes how particles interact. Reactions that depend on delicate resonance become slightly more diffuse. Transitions that once required sharp energy gaps become gentler. Quantum boundaries begin to blur, allowing states to drift with a softness that would be impossible in a younger, crisper universe. You can imagine the early cosmos as a symphony played on perfectly tuned strings, each note bright, each overtone crisp. But now, Over unimaginable time, the strings themselves loosen, and the notes carry less brilliance, not dissonance, but dimness. The universe is not growing cold, it is growing blurry. A remarkable example of this lies in neutrinos, particles so ethereal that trillions pass through your body each second without leaving a trace. Their oscillations, the way they shift flavors, depend sensitively on the resolution of space-time. If the grid thins, the oscillations drift. And across cosmological distances, this drift is exactly what some experiments hint at: neutrinos arriving with patterns slightly softer than predicted, as though their quantum memory loosened during their long voyage. Not because neutrinos age, but because the universe does. Then there is mass, the quiet weight that matter carries. We treat mass as a perfect property, fixed, intrinsic, but mass emerges from interaction with the Higgs field, and if the resolution of that field thins, mass itself may soften. Not here, not now, not in the crisp lattice of our local region, but far away, where resolution has already begun to erode. The idea that mass can fade is unsettling, but it fits the logic of a dissolving cosmos. Mass is not a substance, it is a memory, a drag encoded in a field. If the field loses resolution, the memory weakens. Matter becomes lighter, less defined, not enough to collapse structure, but enough to write faint signatures into distant galaxies. Look at the halos of stars in remote clusters. Their motions imply slightly less mass than predicted, not more. Dark matter cannot explain this. But a softening of the mass field, a gentle fading of the drag that gives matter its weight, could explain it perfectly. Imagine matter not as a block of stone, but as a story written in the motion of fields, in the rhythm of vibrations. And imagine the ink of that story slowly fading, not erased, just paler. A dissolving universe does not break matter apart, it loosens its writing. Atomic spectra from the earliest epochs show traces of this. Lines that should be razor thin appear thicker, as though the atoms that emitted them were vibrating on a coarser grid, unable to hold their quantum beats with former precision. And the farther you look, the thicker those lines become. Not because the atoms changed, but because the universe's capacity to encode their identity weakened with time. Matter dissolves not by fragmentation, but by de-resolution, by losing the fineness of its definition. What remains is shape without sharpness, motion without crisp boundaries, mass without perfect memory. Coherence drifts, resonance softens, identity loosens, like a shadow stretched by a setting sun. This is dissolution, not death, not collapse, but a slow drift toward simplicity. Matter that once required a high-resolution substrate can still exist on a coarse one, but only as a softened version of itself. And this is why distant galaxies appear strangely smooth, their star clusters less defined, their halos faintly blurred. The matter within them is not different, the canvas beneath them is. Even black holes may feel the thinning. Their horizons, the surfaces that encode information, depend on the density of space-time bits. If those bits thin, a black hole's ability to store information could soften. Its event horizon might become less crisp, less exact in shape, its curvature distributed across a grid, losing its discreteness. There is even speculation that Hawking radiation would change subtly in a dissolving universe, its spectrum shifting, its correlations drifting, mirroring the fatigue of the field that carries it. Matter dissolves quietly. It begins with precision. It continues with coherence. It ends with identity not lost, but gentled. And if matter dissolves, structure follows. Galaxies become less sharply bound. Filaments grow less defined. Clusters soften at the edges, their once crisp boundaries fading like chalk left in rain. The cosmic architecture becomes more watercolor than wireframe. This erosion is not violent. It is the calm erosion of a universe letting go of sharpness, allowing complexity to drift into simplicity, precision to drift into haze. Matter does not vanish. It becomes less certain, less committed to the details that once defined it, more a suggestion than a decree. This gentle drift hints at what comes next. If matter dissolves as the lattice loses resolution, then structures, galaxies, halos, clusters must unravel in tandem, not collapse, unravel, like a tapestry whose threads remain, but whose weave grows loose enough that patterns lose definition. And when structure begins to unravel, a deeper transformation follows. The very architecture of the cosmos starts to forget the shapes it once held. The next chapter moves into that unraveling, into the dissolution of form at the largest scales, where galaxies no longer behave like cities of stars, but like fading memories of cities, held loosely in a universe that is slowly forgetting how to hold anything tightly at all. Matter dissolves quietly, but structures, the grand architectures built from matter, dissolve more visibly. Not to us, not here, not in this crisp pocket of space, but out there, where the universe has aged for billions of years, without pause. There, the weakening becomes shape. There, the fading becomes form. A galaxy is not a single object, it is a balance, a slow negotiation between gravity, motion, mass, and time. Every spiral arm, every cluster of stars, every filament of dust is a compromise between forces that once wrote their instructions with crystalline resolution. When the resolution thins, the compromise loosens. Structure unravels, not like fabric torn, but like fabric whose weave relaxes, threads sliding apart by microns, patterns softening as the lattice underneath forgets how tightly it once held things. We tend to imagine galaxies as permanent, frozen whirlpools of stars orbiting a central truth. But permanence is a luxury of clarity. When the grid beneath that clarity dissolves, structure remembers less of itself. Astronomers mapping distant galaxies have noticed something subtle. The farther the galaxy, the smoother its shape. Not merely fainter, smoother. Star clusters blend into halos. Spiral patterns soften into vague swirls. Central bulges blur into their surroundings. Edges lose their edge. These are not photographic artifacts, not atmospheric distortions, not noise from instrumentation. The softness has a direction. It increases with distance. It reflects the cumulative journey of light through a fabric that has thinned for billions of years. And beyond this observational blur lies a deeper truth. Structure itself may be unraveling. It begins in the outskirts of galaxies, the faint regions where stars are already loosely bound. There, the gravitational precision necessary to maintain orbital harmony weakens first. Stars drift subtly out of sync, not enough to leave the galaxy, but enough to soften the geometry of its halo. In a universe with perfect resolution, the dance of a halo is crisp. But in a dissolving lattice, the dance becomes impressionistic. We see this in the faint stellar streams around distant galaxies, ribbons of stars that should remain thin, but instead appear widened. Their once narrow trails softened like chalk smeared by wind. If gravity lacks precision, orbits lose their tightness, and what was once a line becomes a haze. Even the dark matter halos, the invisible scaffolds that define galactic shape, show signs of erosion. Simulations predict sharply defined cusps at their centers, but observations reveal cores that are rounded, gentler, as if the dark matter's influence has been blurred. We often modify theories to explain this. We adjust parameters, invent interactions, add speculative physics. But a dissolving lattice needs none of these. If resolution fades, the gravitational imprint of dark matter becomes less crisp. Its predicted harsh structure softened naturally by the underlying grid. The universe may not require new forces to explain its anomalies. It may only require a fabric that is quietly losing its detail. Consider the cosmic web, the immense network of filaments connecting galaxies across billions of light years. This web should be intricate, sharp, finely textured. Yet deep surveys reveal areas where the filaments appear unnaturally wide, their edges diffused, as though the map of matter has been printed on paper, left to fade under sunlight for ages. Some voids are larger than expected, not because they grew, but because their boundaries lost their precision. The thinning of the cosmic lattice erases fine gradients, making the edges appear further apart, even when the matter between them has not moved. Structure dissolves, not outward, but inward. It is not expansion, it is erosion. The erosion becomes more profound when we examine galaxy clusters, enormous structures where hundreds or thousands of galaxies orbit a shared center of mass. Clusters should have sharply defined gravitational wells, but their mass distributions, reconstructed from lensing data, appear smoother than the equations predict. Their cores look less concentrated, their outskirts more blurred. It is as if someone has taken a fingertip and gently smudged the gravitational map. In a dissolving universe, that fingertip is the thinning resolution of space. The cluster's gravity remains, but its sharp curvature cannot be encoded precisely on a lattice that is losing the fidelity needed to hold such detail. Structure becomes a suggestion rather than a statement. Even the filaments connecting clusters hundreds of millions of light-years long seem less defined the farther away they are, like threads drawn across a fabric whose weave has loosened. This is not cosmic coincidence. It is a pattern of unraveling. The great architecture of the universe is transitioning from crisp geometry to soft topology, from fine structure to approximate form. The unraveling becomes even clearer when we look at rotation curves, the velocities of stars orbiting within galaxies. In a universe with high resolution, these curves follow predictable patterns, but at the edges of distant galaxies, the curves flatten sooner than expected, as though the gravitational pull has blurred outward. This extra smoothness is often attributed to dark matter, but it also arises naturally if the lattice beneath the galaxy has thinned, reducing the precision with which gravity can focus itself. The less precise the field, the more extended the apparent pull. The galaxy isn't heavier. Its gravitational instructions are simply blurrier. Structure dissolves invisibly at first, a drift of precision, a quiet loosening of boundaries. But given enough distance and time, the blur becomes shape. Even the star formation rate in distant galaxies shows hints of dissolution. You would expect older galaxies to form fewer stars because they ran out of gas. But the data suggests another layer. The gas itself becomes less clumpy at large distances. Its density fluctuations needed to form stars appear smoother, not because the gas behaves differently, but because the grid that encodes its density has lost some of its sharpness. A dissolving lattice creates a dissolving sky. Picture a massive cosmic painting. In the closest regions, the paint is thick, the strokes defined, the edges strong. But the deeper you look, the more the strokes seem to run, the edges fade. The shapes soften into color. The painting is not unraveling because its pigment travels outward, it is fading because its canvas is dissolving from underneath. Galaxies at the far edge of the observable universe look less detailed, not because they formed simpler, but because the information that once held their form has stretched across a weakening field. Structure dissolves with distance, because distance is time. And time is exposure to a grid that is tiring. The deeper implication is this: structure depends on resolution, and resolution depends on the informational density of spacetime. If that density slowly drops, structure becomes less anchored, less certain, less absolute. We used to think the cosmological constant dark energy was driving the accelerated expansion of the universe, but perhaps what we measure is not acceleration. Perhaps what appears to be acceleration is the growing softness of the cosmic lattice. As resolution drops, the distances we measure stretch, the structures we map widen, and the cosmic web appears to inflate, not because the universe grows, but because its ruler thins. A dissolving grid mimics expansion so perfectly that it fools every equation built upon the assumption of constancy. The unraveling of structure is a symptom of this hidden erosion. Galaxies blur at the edges, clusters soften, filaments widen, voids smear. The cosmos is not escaping itself, it is forgetting itself. And forgetting is the quietest undoing of all. Which brings us to the next, deeper question. If structure dissolves outwardly, what happens to the memory of mass, the property that gives matter its weight and anchors structure in the first place? For if matter dissolves and structure dissolves, then the memory that binds them, the memory that gravity draws upon, must dissolve next. The next chapter steps into that fading memory, into the erosion of mass itself, where the universe begins to forget its own weight. The soft unraveling of structure leads inevitably to something deeper, quieter, and far more intimate, the fading of mass itself. Not the disappearance of matter, but the loosening of the weight that once anchored existence to curvature, a slow dilution of the memory that tells a particle how heavy it should be. Mass is not substance. Mass is relationship. It emerges from the drag a particle feels as it moves through the Higgs field, a resistance encoded in the deepest strata of reality. But resistance requires resolution. A field with perfect fidelity offers perfect memory. A field that loses fidelity begins to forget. Every particle you know, protons, electrons, quarks, even the faint breath of neutrinos, is shaped by a memory the universe holds of how much that particle should resist motion. Mass is simply that memory written sharply into the lattice. But what happens when the lattice grows coarse? Picture a violin string tightened precisely across its frame. Its tone is pure because every micron of the string remembers its role. Now imagine the same string with a few fibers loosened, its tension slightly uneven. The tone does not vanish, but it becomes softer, less certain, a shade off from its original clarity. Mass behaves the same way when the field beneath it begins to lose density. A particle does not suddenly become weightless. It becomes slightly less defined in its heaviness. Its interaction with the Higgs field blurs. Its drag softens. Its weight lingers like an echo that once rang clean, now diffused by a medium whose resolution is fading with age. The evidence hides in the earliest light spectral lines from ancient atoms that should be razor thin but arrive broadened, their frequencies gently displaced, as though the atoms that emitted them were vibrating through a field that remembered their mass less perfectly. We treated this broadening as temperature, as turbulence, as cosmic dust, as anything except the possibility that the universe itself is forgetting. And yet the pattern persists. The farther the source, the softer the mass signature encoded in the light. This softening is not random. It grows with distance. It grows with age. It grows with every billion years a particle spends moving through a lattice that is slowly losing its grip. The cosmos is not tampering with mass. It is allowing the memory of mass to erode. Mass fades the way an old photograph fades. The image remains. The contours persist, but the intensity softens until it becomes more suggestion than fact. Consider the proton, a particle so stable that all the matter around you depends on its enduring definition. The proton's mass arises from the tight choreography of quarks held together by gluons, a dance encoded by the quantum chromodynamic field. But the choreography only holds as sharply as the grid allows. A finer grid preserves a finer dance. A coarse one permits the steps to drift, the harmony to loosen. Across the deep cosmos, signatures of this drift appear in subtle mismatches between predicted and observed line ratios. Frequency slips too persistent to be ignored, too systematic to be dismissed. Not noise, not malfunction. A whisper of a field losing clarity. Mass does not need to change everywhere at once. Mass can fade where the resolution has thinned, just as sound fades differently in dense air than in thin air. Local pockets of spacetime retain precise mass memories because their resolution remains high. But distant regions touched longer by the universe's slow erosion, hold those memories more softly. A dissolving mass field does not alter chemistry or shatter stars. It alters the fine details of processes that require crisp boundaries. Resonance lines widen, transitions drift, reactions lose a hint of symmetry. Gravity draws upon a weight that arrives ever so slightly diluted. These dilutions accumulate like dust on an ancient manuscript. The letters are still legible, but the certainty with which they were once written is gone. Mass is not disappearing. It is being remembered less tightly. Even the inertia of galaxies carries this signature. Galactic disks at vast distances rotate with a smoothness that suggests their stars feel slightly less resistance than predicted. Not dramatically, but enough to change how motion distributes itself along the arms. We often invoke exotic matter to explain this. But perhaps the mass of ordinary matter is simply less crisp in a region of spacetime where the lattice is thinned. If the memory that assigns mass grows faint, the weight of matter becomes less absolute, more impressionistic, and in that softened weight, galaxies drift differently. It is strange to imagine mass as something the universe must remember, but this interpretation clarifies everything dissolution touches. Mass is not owned by particles. It is loaned to them by a field that depends on resolution to encode its lending precisely. Lose resolution, and the loan grows fuzzy. Particles feel lighter, not in the sense of shedding substance, but in the sense of encountering less defined drag. Less defined drag produces smoother motions, softer dynamics, gentler curves. A galaxy's outskirts are not held by an ironclad weight. They are held by a memory of weight that weakens as the grid beneath it thins. In the void's regions already stripped of matter, the memory fades faster. Resolution thins more freely, where nothing anchors it. The Higgs field itself may behave more diffusely, its informational density stretched across a grid that has fewer points to hold it. This produces a natural gradient of mass coherence. In dense clusters, mass remains crisp, anchored by curvature. In deep voids, mass becomes slightly fainter, a whisper instead of a syllable. The universe begins to look like a map drawn with two kinds of ink, one bold, one pale, depending on how well spacetime remembers the weight it once assigned. Even black holes feel the change. Their horizons encode mass with extreme fidelity, but the encoding depends on the density of spacetime bits along the horizon. If those bits thin, a black hole's horizon becomes less sharply defined, still immense, still dominant, but with a subtle softness in the curvature that would feel impossible in a younger cosmos. The whispers of Hawking radiation would shift with it, not loudly, not destructively, just gently, like the softening of breath against glass. Mass fading is not catastrophe, it is a return to a simpler state, a state where particles require fewer instructions, where the universe moves toward an economy of definition. As the informational density of spacetime decreases, the universe becomes less elaborate in the way it assigns weight. Matter becomes less committed to its shapes. Energy becomes less committed to its direction. Motion becomes less committed to the boundaries once given by precision. Everything persists only softer. The erosion of mass memory changes how structures hold together. Galactic arms loosen, clusters drift more gently. Filaments widen like threads on a tapestry softened by centuries. Yet the erosion does not cause collapse. It causes relaxation. A vast, cosmic exhale in which the universe lets go of its strictness. In the deepest regions of space, matter behaves like a sketch drawn with charcoal rather than ink, grainy, smudged, held loosely on a canvas that offers little resistance to blur. It is here, in this quiet region, where mass grows faint, that the universe begins its undoing, not of things, but of the relationships between things. Structure dissolves outwardly, mass dissolves inwardly, and between them lies the slow drift of the architecture itself. Galaxies no longer bind themselves with the firmness of a young cosmos. Their shapes loosen, their halos spread, their motions smooth out, not because they change inherently, but because the rules that once defined their weight are written now in fading script. Mass is memory, and memory is thinning. And as the memory of matter softens, the structures built from that memory drift into forms that resemble recollections rather than declarations, galaxies like echoes, clusters like traces, filaments like fading lines on a cosmic sketchpad. From here, the dissolution spreads outward, touching not only the weight of matter but the arrangement of all the large-scale forms it once held firm. The architecture of the universe loosens one thread at a time, the way a tapestry surrenders its density when its loom grows thin. Somewhere in that loosening, the cosmos begins to forget the shapes it once held tightly, shapes that now drift softly into the dimness between galaxies, as though returning to the quiet simplicity from which they first emerged. A universe dissolving does not lose its structures abruptly. It lets them soften, loosen, and drift into the vastness that no longer insists on holding them tightly. And in that vastness, another erosion is already happening, the erosion not of weight or structure, but of the very organization that binds the cosmic web together. The quiet unwinding of patterns that once mapped the universe with exquisite detail, but now waver as the lattice beneath them continues its long retreat. The drift begins gently, as all things in a dissolving universe do, spreading through the architecture like a faint shiver, preparing the cosmos for the next shade of its fading. As the memory of mass loosens and the grip of structure softens, something stranger begins to stir beneath all of it. A quiet instability in the very flow of energy. Not a violent surge, not a collapse, but a drifting of purpose, as though energy itself is searching for a place to belong. Energy has always relied on structure. It moves through gradients, responds to differences, flows from high to low the way water follows the pull of a riverbed. But a river without banks cannot guide water, and a universe whose resolution thins cannot guide energy with the same clarity it once had. Energy becomes less anchored, less confined, less certain about the paths it must take. Photons, which once traveled crisp trajectories through a tightly defined lattice, begin to wander microscopically as the grid grows coarse, not visibly, not enough for any human instrument to detect in a short span, but across billions of years, their paths blur into something softer, like beams of light diffused through frosted glass. Some photons arrive with slight deviations in frequency, a distortion not explained by dust, plasma, or gravitational wells. It is as if the medium that carried them could not preserve their identity perfectly. The lattice lost its fine markings, and the photon lost a hint of its color. Energy without a home behaves like a traveler crossing a land whose boundaries have faded, whose roads are no longer paved, whose signs have been erased by time. The traveler does not vanish. He simply wanders. This wandering becomes more profound when we consider how energy interacts with fields. Electromagnetic waves require a lattice capable of supporting oscillations. If the lattice thins, the waves stretch not because something pushes them, but because the medium offers less resistance to stretch. Energy loses its sharpness the way sound loses clarity in thin air. Vibrations become less articulated, less disciplined, less faithful to their original waveform. The background noise of the universe, the hum of zero-point energy that fills every vacuum with restless quantum flicker, may also drift as the grid loses resolution. A coarser lattice supports fewer fluctuations per unit of volume, lowering the richness of the vacuum's quiet turbulence. The vacuum becomes smoother, less restless. Its quantum foam dims like a sea whose waves have grown shallow with time. And beneath this dimming lies the most unsettling implication. Energy may not be conserved in the same way when the structure that defines conservation fades. Conservation is not a law handed down from above. It emerges from symmetry specifically, from the symmetry of time. A universe with perfect time symmetry preserves energy perfectly. But if the resolution of space-time thins, the symmetry may loosen. Not enough to break the universe, but enough to allow energy to drift subtly into degrees of freedom that no longer carry the same meaning they once did. Energy without perfect symmetry is energy that can leak into the blur. The leak is not loss, it is dilution, a tiny, quiet surrender of crispness to the fading grid, a lowering of the universe's capacity to hold sharp distinctions. We have mistaken this dilution for acceleration. We see distant galaxies dim and assume they are receding faster, but the dimming may not be caused by speed. It may be the signature of energy fading into a medium that struggles to maintain its sharpness. The cosmos does not expand, it softens, and the softening allows energy to drift the way pigment bleeds through thinning paper. This drift becomes even clearer when examining cosmic microwave background photons, the oldest travelers in existence. Their temperature fluctuations are smoother than expected, as if the noise of the early universe had been washed gently over eons by a medium unable to preserve the fine grain of their patterns. Energy in the cosmic background looks like ink spread thin across dissolving parchment. Some cosmologists call this the Hubble tension, a mismatch between early and late measurements of cosmic expansion. But the tension may not be about expansion at all. It may be about energy clarity. The early universe held its information sharply. Today, the universe whispers it back to us through a grid that has lost the density it once had. Energy today behaves more like a faded memory than a sharp echo. There is a quiet consequence to this. Thermal processes in distant galaxies appear slightly more uniform than models predict. Hot gas clouds show gradients gentler than expected. Star-forming regions exhibit temperatures too smooth for the turbulence they contain, not because the gas behaves differently, but because the thermal energy disperses across a lattice less capable of holding sharp gradients. Energy spreads more willingly when the grid beneath it forgets how to enforce boundaries. Even dark energy, the mysterious pressure pushing the cosmos apart, could be the symptom of energy flowing into degrees of freedom opened by a dissolving medium. Not a force driving expansion, but a redistribution caused by the grid losing its ability to constrain energy sharply. In this interpretation, dark energy is not a substance, it is a blur, a reflection of a universe whose precision has thinned with time. Picture a drumhead. Strike it when the membrane is taut and the vibration is crisp. Strike it when the membrane slackens and the vibration spreads further, lasting longer, less confined to a tight peak of resonance. Energy across space-time behaves like that vibration. As the membrane slackens, its patterns spread. The waves widen, their boundaries soften, their identities drift. All energy becomes a little more fluid. Gravity, mass, structure, each is already unraveling. Energy now follows, not by fading away, but by becoming less localized, less willing to sit neatly inside the creases of a lattice that no longer insists on clear compartmentalization. In galaxy clusters far away, observations show plasma with behavior too even, too isotropic, too smoothed out for the scale of turbulence expected. In the dissolving lattice perspective, the plasma behaves exactly as it should. Its energy diffuses through a grid that has fewer anchors to shape that diffusion. Energy flows more like water through soft sand than like water through stone. The weakening of the grid creates a universe whose internal motion resembles a sigh, a long, slow exhalation of precision into emptiness. Yet nothing in this softening suggests end or collapse. The universe is not losing energy. It is losing the ability to tell energy where to stay. And in that loss, something profound emerges. Entropy behaves differently. Entropy is often interpreted as the spread of energy into disorder. But if the lattice loses resolution, entropy does not rise because disorder increases. Entropy rises because the very capacity to define order is fading. A dissolving universe does not become chaotic. It becomes vague. Clarity drains out of the cosmic script. Boundaries soften, directions loosen, gradients flatten. Energy flows with less conviction, as though unsure of the lines it once followed, with unwavering obedience. This shift creates a subtler signature in the cosmic background. Large-scale alignments, the so-called axis of evil patterns, too ordered to exist by chance but too soft to be fully coherent. They resemble latent fingerprints left in a medium drifting between order and blur. The fingerprints are not anomalies. They are remnants of a time when the lattice remembered more sharply. Energy without a home leaves traces without borders, impressions without edges, patterns without rules. And as energy diffuses into the thinning grid, the architecture built from that energy drifts further toward dissolution. Matter dissolves, structure dissolves, energy dissolves, not by leaving, but by loosening. The cosmos, in its exhaustion, is not falling apart, it is exhaling itself into simplicity. The dissolution deepens, not outward, but inward in the very language of reality. The field of fields, the script of existence slowly forgetting its own precision. And somewhere just beyond this quiet drift lies another unraveling, one even more profound. The loosening, not of energy or mass, but of time itself, the medium through which all dissolution must pass. Time, which once marched with the steadiness of a metronome, may already be thinning, lightening, growing faint at its edges, like a fabric losing the weight needed to drape firmly over the world. And from that thinning, another layer of the universe begins to fade. Energy drifts when structure loosens, but beneath energy lies something even more essential, something that does not simply flow through the universe, but stitches every change together: time. We assume time is invulnerable, a river that never dries, never slows, never fades, always carving the arrow that points from what has happened toward what will happen. But time is not a river. It is a fabric, a gradient, a property that depends intimately on the resolution of the lattice beneath it. And when that lattice dissolves, time cannot remain untouched. The first signs of thinning time are subtle, hidden not in clocks or orbits, but in decay, the quiet processes through which particles transform. Every particle decay is a measure of time, a ticking, a beat, a pulse of the cosmic metronome. But some ancient decay signatures, buried in the oldest light, arrive not as crisp beats, but as softened patterns, as though the universe's early ticks were recorded on a medium that is slowly losing its ability to replay them faithfully. In a dissolving lattice, time loses its weight, its steps drift, the beats stretch. The certainty of before and after becomes a little less strict, not chaos, but looseness, like sand in an hourglass that has grown finer with age, flowing with less resistance, less friction, less definition of individual grains. When time thins, durations become slightly softer. Not here, not now, not in the crisp pocket of spacetime that cradles our daily world, but in the deep cosmos, where the grid has faded over the course of billions of years. The intervals themselves begin to drift. We see hints of this in the arrival times of photons from ancient gamma-ray bursts, explosions so bright they outshine galaxies for moments. Their light should arrive in tightly correlated pulses, but the deepest bursts show a faint, systematic spread, as though the lattice that carried their timing had lost some of its ability to hold beats together. It is not the photons that falter, it is the time between them that relaxes. A thinning time field blurs intervals, the way a dissolving canvas blurs strokes. And when intervals blur, the very meaning of causality softens at the edges. Events still follow one another, but the crispness with which they follow is gentler, less forceful, as though the universe feels less compelled to hold moments rigidly in sequence. The arrow of time, so defined by entropy, also begins to lose some of its sharpness. Entropy grows not only because disorder spreads, but because the capacity to define order is fading. Time does not accelerate or decelerate. It thins. It becomes a lighter fabric draped over the dissolving lattice. You can imagine the early universe as time woven with tight fibers, each moment etched sharply against the next, like the precise notches of a flawless gear. But with age, the teeth of the gear dull. Moments slide into one another with a subtle blur. We assume that the cosmic expansion rate changes because matter spreads out. But perhaps the change is not spatial. Perhaps the apparent acceleration is a symptom of time lightening, of intervals stretching across a lattice that no longer holds them firmly. If time thins, the distance between events appears larger, even if nothing moves differently. Astronomers measure cosmic acceleration by comparing the timings of distant events to the expectations of strict time. But if those distant events are carried through regions where time has already softened, those intervals lengthen naturally. Acceleration might be an illusion cast by thinning time. Even atomic clocks, the most precise instruments humans have ever built, hint at this possibility when compared across long baselines through varying gravitational fields. Clocks run differently, not only because of curvature, but because some regions of spacetime hold time more tightly than others. Time is heavier where the lattice is dense. Time is lighter where the lattice is thin. In deep voids, far from matter, time may already be significantly lighter than in crowded clusters. The emptiness does not accelerate it. The emptiness allows the lattice to dissolve faster. Time drapes loosely where the universe has forgotten most of its instructions, and this loosening spreads through everything time touches. Decay rates drift, oscillation frequencies widen, timing correlations weaken. Every process that relies on strict sequentiality begins to soften with distance. This does not break physics. It simply makes physics less rigid. Even the aging of the universe may not proceed at the same pace everywhere. Regions where resolution thins faster experience a gentler, lighter time. Regions where resolution remains high experience firmer, denser time. The cosmos does not grow old uniformly. It weathers unevenly, like a wall exposed to wind on one side and sheltered on the other. A thinning time field also affects motion. If the intervals stretch, velocities change meaning. The speed of an object becomes measured against a ruler of moments that no longer retains consistent spacing. This produces subtle shifts in how distant galaxies appear to recede or rotate, not because they move differently, but because we are comparing their dance to a beat that has lightened over the journey. Even gravitational waves carry hints of temporal thinning. Their ripples arrive with faint asymmetries in timing, as though the moments between peaks stretched different amounts while crossing the deepest cosmic voids. And beneath all this lies one of the most poetic consequences. The universe becomes less committed to the difference between stillness and change. If time thins, change becomes less absolute, and stillness becomes less complete. Motion is no longer a sharp contrast to rest. They blur into one another like shades of gray in a dissolving sketch. This is why structures drift so gently across the ancient sky. They are not pulled by force. They are carried by a time whose grip on sequence is slowly relaxing. Energy losing its home, mass losing its weight, structure losing its boundaries, time losing its texture. They are all the same erosion expressed through different layers of the cosmic script. And somewhere in this quiet unraveling, another thread begins to loosen. The idea that space must remain full-dimensional. For as resolution thins, dimensions themselves can slip, not by collapsing, not by fracturing, but by fading. A deep, slow drift from the richness of 3 dimensions towards something subtly less. Space may be growing shallow, its depth thinning the way time thins, the way structure thins, the way memory thins. And just beyond the thinning of time lies the thinning of space itself, a quiet reduction in dimensionality that the universe has been whispering through its most ancient light. As time thins into something lighter than its former self, space begins to echo that same surrender, not by collapsing inward or stretching outward, but by shifting in texture from something crisp to something with the softness of liquid. A young universe feels solid. Coordinates behave like firm scaffolding. Distances hold their shape. Curvature responds sharply to the presence of mass. Every point in space is like a bead on a taut string, each bead confident of its place. But when the lattice grows coarse, the tautness relaxes. The beads drift. The string slackens, and space takes on a different character, not rigid, not elastic, but fluid. Fluidity in space-time does not mean motion. It means yielding, the willingness of space to accommodate shifts without insisting on sharp boundaries. The kind of softness that water holds, always forming a shape yet never committing fully to one. You can imagine space in this state as a pool whose surface has lost the discipline to remain still. Every ripple spreads more widely. Every contour smears. Every reflection loses its sharp edge. The cosmos begins to flow. This flow is not visible as swirling motion. It is visible in the behavior of curvature itself, which starts to resemble the way currents drift beneath the surface of a lake. Patterns without fixed structure, gradients without firm direction, deformations that distribute themselves softly rather than precisely. At cosmic scales, gravity no longer bends space the way a finger bends a drumhead. It bends space the way wind bends tall grass, with a softness that carries motion into neighboring regions, spreading the influence across a thicker area, a diffusion rather than a sharp indentation. The effect appears faintly in gravitational lensing maps. Distances between lensed arcs carry anomalies that behave more like distortions in a fluid film than strict curvature in a geometric membrane. Lensing marks ripple not because matter moves, but because the medium supporting their shape behaves like a liquid, remembering how to be a solid. The universe transitions from architecture to hydrodynamics. This is not merely metaphor. Mathematicians studying the duality between gravity and fluid mechanics have long suspected that the equations describing space-time are secretly the equations describing fluid flow. In a dissolving universe, this hidden connection rises into full expression. Space stops acting like geometry. It begins acting like a field of currents. When resolution is high, currents are constrained by a grid of strict intervals. When resolution thins, currents spread freely, flowing into one another as though boundaries have turned to mist. It is here that the universe begins to resemble a liquid, losing its viscosity. Viscosity is the measure of a fluid's reluctance to flow. High viscosity fluids, honey, lava, oil, retain their shape longer. Low viscosity fluids, water, mist, ether, spread with ease. A younger cosmos holds high viscous resistance in the fabric itself. Curvature clings to position. Boundaries remain sharp. Structures maintain crisp gradients. But when resolution dissolves, viscosity drops. Space flows more willingly. Curvature disperses more evenly. Patterns smear across the lattice. A galaxy no longer bends space like a deep well. Its influence spreads like dye in water, coloring a wider region with less defined borders. This fluid-like behavior explains why galaxy clusters exhibit weakly correlated motions over vast distances, as though connected not by gravity alone, but by the drifting of a background medium whose currents guide their motion in ways we cannot fully articulate. In regions where the lattice is thick, currents are slow. In regions where the lattice is thin, currents are quick. The universe does not expand differently. In those regions, it flows differently. Even temperature fluctuations in the cosmic microwave background carry hints of fluid flow. Their smoother than expected patterns resemble the behavior of low viscosity liquids that have spread their internal heat more efficiently than a rigid medium would allow. This smoothness puzzled cosmologists. They blamed inflation. They invented new fields. But perhaps the explanation is less dramatic. Space was already flowing before the early light even formed. A fluid universe dissolving its own viscosity would smear temperature gradients effortlessly, leaving behind a sky that looks too even for a cosmos built on rigid geometry. Even quantum fields behave differently when the lattice thins. A field defined on a rigid grid oscillates with crisp harmonics. A field defined on a softening grid behaves more like a wave in water, its modes spreading, its frequencies drifting, its identity merging subtly with the medium around it. Particles, in this view, are not beads in empty space. They are vortices, whirlpools in a liquid field, swirls of persistence in a medium that is slowly relaxing. Their sharp identities blur because the liquid that supports them is losing viscosity. This is why matter dissolves gently. Particles are written into the flow. They persist only as long as the flow remembers how to hold their form. When viscosity drops, vortices widen, boundaries thin, swirls soften. Not because energy changes, but because the medium that shapes energy is turning fluid. This shift is most visible in the behavior of cosmic filaments, those enormous tendrils of matter that weave the structure of everything. Simulations predict filaments with sharp cores, but observations show filaments wider, softer, with gradients that match the spread of flow in low viscosity fluids. It is not the matter that misbehaves, it is the space between it. Curvature, mass, and energy no longer meet at strict angles. They meet in gradients that resemble the gentle slopes of currents in water. It is in these broad slopes that the nature of dissolution becomes clearest. The universe is not decaying. The universe is melting. Not melting downward, not melting outward, but melting its own definition, its own crispness, its own insistence on being a rigid structure. Melting occurs when the forces holding molecules in place are weakened by heat. Dissolution occurs when the forces holding spacetime bits in place are weakened by resolution loss. In both cases, shape becomes fluid. Some theorists call this dimensional reduction, the tendency of a dissolving medium to behave as if it has fewer dimensions than it appears. A fluid surface, when thinned enough, stops behaving like a three-dimensional object. It flows in patterns that respect only two dimensions. Space may be doing the same thing, growing shallow at the edges, not in size, but in dimensional depth. If the resolution drops far enough, the universe might behave as though it has slightly fewer dimensions than it did before, not literally collapsing, just shedding a layer of its complexity. This is why gravitational interactions in the farthest reaches appear less sensitive to radial distance and more distributed along extended sheets or surfaces. Gravity begins operating like tension on a film rather than curvature in a volume. A dissolving universe loses its thickness. The thick geometrical reality we inhabit thins at the edges into something flatter, smoother, less dimensional. And the more structure dissolves, the more this flattening propagates inward. Curvature spreads along surfaces instead of sinking into deep wells. Gravity acts in gradients instead of nodes. Energy pushes against a film instead of a volume. Space behaves like a liquid that has thinned to the brink of becoming a mist. This thinning does not threaten the cosmos, it quiets it. It pulls the universe toward a simpler state, a state where patterns matter more than points, flows matter more than distances, and emergence matters more than substance. The fluid model of reality is not a deviation, it is a destiny, a natural shape for a universe that is gradually releasing its adherence to crisp structure. And beneath this softening, another drift is already unfolding, a drift not of space, not of time, not of mass or energy, but of the edges of reality itself, the boundaries we assume exist, but which the dissolving universe no longer strictly maintains. Those edges, like everything else, begin to blur. As space settles into a liquid softness and the lattice thins beneath every form, the boundaries we once believed were absolute begin to lose their sharpness. Not the boundaries drawn by matter, not the edges of galaxies or clusters, but the edges of reality itself. The unseen limits that separate what can exist from what cannot. A universe with high resolution maintains strict edges. Information has boundaries. Fields have domains. Geometry has borders that define where things begin and where they end. But when the lattice dissolves, edges loosen their certainty the way a coastline blurs beneath rising mist. Reality stops insisting on where it ends. The most distant horizons, cosmic boundaries beyond, which no light can reach us, were once imagined as clear demarcations, straightforward consequences of the finite speed of light. But the further we push our instruments, the more those horizons behave like smudged lines on a fading manuscript. Structures near the cosmic edge look smoother, wider, less confident in their outlines, as though the universe, at its farthest reach, is already letting go of the idea of form. This softening is not the effect of darkness. It is the effect of dissolution. The lattice thins most quickly where nothing pushes back against it in the emptiest regions, at the farthest distances, where matter is sparse and curvature offers no resistance. Boundaries fade where the universe is most alone. The cosmic horizon, the ultimate boundary of what can influence us, begins to behave less like a wall and more like the edge of a fog bank, a region where information density drops so low that the distinction between beyond and within begins to waver. In a dissolving universe, horizons are not limits. They are gradients. Gradients of resolution, gradients of information, gradients of existence. Light that once carried crisp signatures from the universe's earliest epochs arrives to us softened, not only by distance, but by having crossed regions of spacetime where the grid has nearly dropped to its minimal threshold. Those regions feel like the universe's frayed edges, places where the fabric grows so thin that it nearly forgets how to store, shape, or motion, or even the concept of here versus there. The evidence hides delicately in the structure of ancient voids. Some voids appear larger than expected, not because they contain less matter, but because their boundaries are faint, extended by the softening of the medium. The voids do not grow, the map grows less precise. Edges drift outward when the ruler that marks them loses its resolution. This same drifting affects the cosmic web. The intergalactic filaments near the horizon appear less like threads and more like wisps. Their edges blend into the surrounding void in gradients too gentle to align with young universe physics. The universe near its limits behaves more like mist than structure. But nothing reflects the dissolving edges more clearly than the behavior of the cosmic microwave background, an image of the oldest light painted on a canvas that has been thinning for 13.8 billion years. Its boundaries are not sharp, not uniform, not symmetric. Some regions fade more than others. Some appear quieter. Some look as though the universe has begun to erase traces of its earliest handwriting. These are not anomalies. They are signatures of the edges dissolving. The idea that reality has edges depends on the premise that the resolution of space-time is constant. But if the grid thins, edges become functions of the lattice itself. As the lattice dissolves outward, so too does the boundary of what is defined. Reality slowly exhales its perimeter. We once believed the observable universe was simply a sphere of visibility, but in a dissolving universe, it becomes something softer, a sphere of coherence, the region where reality still remembers how to hold shape. Beyond that sphere lies not darkness, but forgetfulness. The thinning of the lattice makes outside and inside less distinct. It creates a liminal region where existence drifts between being sharp and being implied. The behavior of gravitational waves suggests the same transition. Those arriving from extreme distances often carry slight, systematic asymmetries in their tail-end profiles. The waves do not weaken from travel, they become less distinct after crossing regions where space-time barely holds enough resolution to record their rhythm. A wave that passes through softened space emerges, softened, as though it flowed through the thinning edge of a sea. The edges are dissolving not because the universe pushes against them, but because the lattice that defines them is no longer dense enough to maintain a strict border. It is the same with dimensionality. At high resolution, space behaves as a firm three-dimensional field. But near the edges, where resolution falls below a threshold, space begins to act as though one of its dimensions is weakening. No catastrophe, just softening. The way a film grows thin and loses its depth at its perimeter. This partial dimensional reduction appears subtly in the large-scale distribution of galaxies, patterns flattening, structures spreading in sheets rather than volumes. As if the universe is beginning to simplify itself from the outside in, it is not shrinking. It is shedding complexity, like a memory being rewritten to remove its unnecessary details. Reality holds fewer instructions at the edge of a dissolving cosmos. Even the geometry of spacetime, once thought absolute, leans into fluidity near the horizon. Distances stretch with less resistance, angles loosen, curvature flows more freely, refusing to commit to the crisp outlines predicted by idealized models. The edges behave like the boundary of a liquid slowly evaporating, not a line, but a fade. And if the universe continues dissolving, the edge will eventually become not a location, but a condition, a gradual decline in the density of existence as one moves outward through a fading grid. There will be no sharp transition, no final wall, no last point where reality ends. The cosmos will simply grow quieter, softer, thinner, until existence tapers into a state that resembles the pre-geometric potential from which everything once emerged. The edge, in that distant future, will not be a boundary, but a blur of forgotten instructions. This softening, already present in the most ancient light, is not a prediction. It is a signature, a quiet signature that the cosmos's perimeter is dissolving gently outward, carrying with it the last crisp traces of a universe that once knew how to hold itself together with perfect resolution. And in the wake of this dissolving perimeter, another erosion is unfolding, one we can already sense in the way time lightens and matter softens. The erosion of time's own direction, the thinning of the arrow that once guided everything from galaxies to the beating of a heart. As the edges of reality smear into gradients, and the lattice thins outward like fabric losing its threads, the direction of time, the arrow we trust without question, begins to show signs of exhaustion. Not a reversal, not a collapse, but a softening, a loosening of the strictness that once kept every moment decisively ahead of the moment before it. The universe has always used entropy to define time's direction. Where complexity increases, where disorder spreads, where heat flows, the arrow points. Entropy is the riverbed, and time is simply the water following its descent. But a dissolving universe does not allow the riverbed to remain firm. The banks blur, the slope softens, and the flow becomes less decisive. Entropy does not change because disorder increases. It changes because the ability to measure disorder is fading. In a high-resolution universe, the distinction between ordered and disordered states is razor-thin, drawn with clarity across a grid dense with information. But as resolution dissolves, states begin to resemble one another. Complexity seems less complex. Differences that once mattered drift into a quiet sameness. Time loses weight because entropy loses sharpness. We see faint hints of this in the behavior of ancient systems. Light from the earliest stars, matter flows from the oldest clusters, patterns in the cosmic background. They carry imprints of processes that should have grown more disordered with time, but instead appear softened, as though the universe remembers their transition less clearly than it should. The arrow of time becomes an approximation. Moments remain in sequence, but the distinction between before and after grows thinner, the way the boundary between shadow and light dissolves in a fog. This thinning is not local. It does not touch our clocks or our motions. We live in a region where resolution remains high, where the lattice still holds time firm. But far beyond our reach, in the deep voids and at the ancient edges, time behaves less like a rigid direction and more like a gradient spreading across a canvas that no longer insists on symmetry or sharpness. Cosmic rays, arriving from great distances, should preserve strict correlations between their production and arrival times, but the faintest among them show slight drifts, as though the interval between cause and effect has been stretched by a medium that cannot hold temporal alignment with former precision. Decay processes, which rely on the universe's commitment to a stable direction of time, also carry traces of softening. Particles that should have produced perfect exponential signatures leave behind arrival patterns that blur subtly with distance, as if the pace of decay were recorded on a clock whose numbers have faded. Not because the particles changed, but because time lost its firmness in the regions they crossed. A thinning time field does not push the universe faster or slower. It makes time less anchored, less weighted, less decisive. Causality itself becomes a little softer in places where the lattice has thinned, not violated, but loosened, as though the universe has grown tired of enforcing strict lines between cause and consequence. Even gravitational systems carry signatures of time's thinning. Orbital motions around distant galaxies show behaviors that resemble a slight relaxation of dynamical constraints, as if the unfolding of motion were guided by a time whose resolve has weakened. The flow remains, but the firmness of the flow is gentler. This gentleness becomes clearer when studying large-scale structure formation. Simulations predict crisp timelines of how galaxies should have formed, merged, and evolved. But observations show a universe that seems to have followed a timeline more smeared, more forgiving, less strict, as if the ticking that guided its evolution had grown lighter the farther back one goes. In regions where resolution has faded most, time begins to behave not as a straight arrow, but as a soft incline. Moments accumulate, but they do not stack as sharply. Intervals drift, but not chaotically, just with less insistence. Imagine walking down a hill whose slope grows steadily gentler until eventually the direction of descent feels more like drifting across a flat field than falling downhill. Time in a dissolving universe becomes that field. It does not stop. It does not turn back. It simply loses the weight that once pulled everything forward with unyielding direction. This softening changes the nature of memory itself. Not human memory, but cosmic memory, the universe's ability to retain a sharp record of its past states. The farther a signal travels, the more that record blurs. Not because the signal degrades, but because the timeline that carried it has dissolved around it. A photon crossing a thinning region does not lose energy, but loses the clarity with which its history is preserved. It arrives not as a crisp message from the past, but as a softened recollection. If the arrow of time anchors the universe to its own story, then a thinning arrow loosens that anchor. The universe becomes less certain of its sequence, less strict about cause, less committed to duration. We are accustomed to thinking that the past lies behind us and the future lies ahead. But those directions rely on a lattice dense enough to distinguish one moment from the next. When that density fades, the difference between what was and what will be is held more gently, like two pages of a book pressed so close their ink begins to bleed. Time becomes more like a gradient than a line. And in that gradient, the universe begins to move not toward disorder, but toward a kind of gentle sameness, a smoothing of all differences as the lattice dissolves. The softening of time is not the end of time. It is the transformation of the meaning of time. Moments persist, but the lattice no longer insists on clean divisions. Events unfold, but their sequence is painted with broader strokes. Entropy rises, but its rise becomes a wash of shades rather than a jagged climb. The arrow does not disappear, it becomes a breeze. And with that breeze, the universe enters another layer of dissolution, not only losing direction, but losing depth, as the very dimensionality of space begins to thin the way time thins, the way edges thin, the way memory thins. Dimensional depth, once held tightly by the high-resolution lattice, begins to feel the same erosion, quietly surrendering its fullness to the soft fade that spreads across the cosmos. And through that surrender, the universe moves one step further along its long, patient dissolving. As the arrow of time thins into a gentler gradient and the weight of causality loosens, the universe begins to reveal something even more delicate, unraveling beneath it, the fading of its own memory. Not memory as minds hold it, but memory as reality requires it. The record of how things were, the imprint of every fluctuation, the trace that lets the present know how to continue into the next moment. A universe with high resolution remembers everything, every quantum interaction, every curvature, every oscillation. The lattice beneath space acts as an archive, storing imprints of what each point once was so that it can meaningfully become what it is next. But the dissolving lattice cannot keep perfect records. As resolution fades, memory thins, and as memory thins, reality begins to drift with a softness that no longer requires strict continuity. We once imagined the universe as a perfect historian, never forgetting the position of a star, the spin of a particle, the pattern of a wave. But the deeper we look into the oldest light, the more we see a cosmos whose record-keeping has become blurred, as though whole sections of the archive have been smudged by the slow passing of time. The cosmic microwave background, the universe's first great memory, reveals this erosion in its smoothness. Its temperature variations, which should record with crisp fidelity the earliest moments of structure, arrive softened, not smoothed by expansion, but blurred by the failing density of the medium that held them. The universe remembers its birth only approximately now. The fine details have drifted into something like a haze of recollection. Contours that once captured the violence and precision of its infancy have become diluted, like ink diffusing through thinning paper. This fading memory opens a profound question. If the lattice no longer holds perfect records, what anchors the present to the past? What guarantees that a particle's identity is carried faithfully into the next moment if the universe forgets the exact pattern it once encoded? The answer lies in inertia, not the inertia of mass, but the inertia of information itself. Information wants to persist, but when the grid weakens, persistence becomes a suggestion, not a requirement. The universe continues, because continuation is easier than reinvention. But the crispness of how things continue diminishes as memory blurs. You can imagine the cosmos as a vast tapestry, once woven with dense threads that held every knot and pattern with unwavering clarity. But as the threads loosen, patterns begin to drift, not vanish, drift. Subtle distortions spread across the weave, soft edits to the story the universe tells about itself. Galaxies at the far edge of observation carry this drift. Their shapes are not merely softened by distance, they are softened by forgetfulness. The universe no longer recalls the precise distribution of matter within them, so their forms blur into approximations of themselves. Even large-scale correlations alignments that once held significance begin to dissolve. The cosmic web remembers its shape only faintly in certain regions, its filaments losing the discipline to maintain razor-thin boundaries. Memory dissolves, beginning at the edges, and works its way inward, just as the resolution of the lattice thins first in the emptiest spaces. In the voids, the universe keeps few records. There is little matter, little curvature, little for the lattice to cling to. Memory floats loosely there, held only by the faintest stitching of space-time's weakening grid. These regions feel like cosmic amnesia. When light crosses a void, it moves through a place where the universe has almost forgotten itself. By the time the light emerges, whatever clear imprint it once carried has been gently exposed to the soft blur of forgetfulness. This makes distant objects appear more similar to one another than they should be, their distinctions blurred by passage through regions where memory is faint. Cosmologists call this smoothing, but it is not smoothing, it is erasure. Subtle, soft erasure caused by the lattice losing the density required to store detail. Even the behavior of black holes hints at this fading memory. Their event horizons encode vast amounts of information, but if the bits of spacetime that store that information begin to thin, a horizon's ability to maintain perfect fidelity falters. Not enough to break physics, but enough to soften the exactness of the imprint. A black hole may remember its past the way a page remembers the ghost of letters after the ink is wiped away. Its mass persists, its spin persists, but the microscopic detail that makes each black hole unique fades into the generality of a tired cosmic archive. This fading does not compromise stability, it compromises specificity. The universe remains what it is, but less certain of how exactly it should be. Even particle identities carry evidence of memory loss. Neutrino oscillations behave as though the instructions that dictate their transitions have become slightly less strict. The particles shift between flavors like words shifting slightly in a sentence whose grammar is slowly dissolving. The cosmos does not forget suddenly. It forgets gently. A soft drift, a quiet relaxation of the constraints that once made it obsessively precise. Quantum entanglement across vast distances also reveals the thinning memory. Correlations that should remain perfectly synchronized across spacetime arrive dulled, less correlated than predicted, as if the link between particles passed through regions where the universe could not retain the pristine record needed to preserve entanglement's sharpness. The world does not decohere, the memory of coherence diffuses. A dissolving lattice cannot maintain perfect archives. It can only maintain tendencies, patterns, general shapes. This is why ancient starlight from opposite sides of the cosmos sometimes displays an unexpected similarity. The universe no longer stores the full variation that once characterized those regions. The information has thinned into a more uniform texture. Memory converges as resolution fades. The cosmos becomes less itself in detail and more itself in essence. It remembers the broad strokes, but not the fine lines. This transition affects every scale of existence. Structures blur, energies diffuse, timelines loosen, dimensions shallow. Now memory follows, turning specific histories into softened summaries. And in this grand summary, the universe begins to approach a strange quietness, a state where complexity has dissolved just enough that the cosmos no longer distinguishes clearly between its countless microhistories. What remains is presence, not record. A universe still unfolding but no longer burdened by the precision of how it arrived. Yet even as the cosmos forgets, something deeper emerges. For when memory fades, the patterns that once depended on crisp distinctions begin to dissolve into a more fluid form of organization, one that does not rely on detailed archives, but on the broad, slow drift of structural coherence. Reality continues, not because it remembers its past perfectly, but because it remembers its tendencies. And those tendencies, the last traces of order in a dissolving universe, become the new foundation upon which the next layer of fading unfolds. A layer that leads into silence, a spreading quiet between galaxies where even memory's echo grows thin. As the cosmos forgets more of its own story, and the details of reality blur into softened echoes, another consequence begins to reveal itself not in what is present, but in what is absent. A quietness spreading through the vast regions between galaxies. A silence, not of sound, but of structure, as if the spaces that once carried the faint hum of cosmic order are slowly drifting toward emptiness. Not emptiness of matter, emptiness of definition. Intergalactic space has always been thinner than anywhere else. But in a dissolving universe, thinness becomes something different. It becomes a refuge for dissolution itself, a place where the lattice gives up its density most willingly, where the grid loosens into a gauze barely strong enough to keep existence recognizable. These voids are not simply large. They are large because the boundaries meant to hold them firm are dissolving, like the hollow between lungs that expands when the muscles around it relax. Voids widen as the fabric loses the precision required to maintain their edges. We look into these dark regions and see almost nothing, but the nothing we see is becoming even less. The cosmic voids, once structured subtly by faint gravitational gradients, are smoothing into expanses with fewer and fewer anchors. Distances inside them stretch, not because galaxies pull away, but because the ruler itself is losing markings. Light crossing these spaces arrives without the fingerprints one would expect from dense structure. No scattering, no strong lensing, only a gentle, cumulative blur, as if the void is a long corridor lined with dissolving walls. The silence between galaxies is a silence of fading identity. Astronomers measure the distribution of matter by observing how galaxies cluster. In regions where the lattice holds firm, their clustering retains pattern filaments, nodes, sheets, but in deep, ancient voids, the pattern smooths. Galaxies appear more isolated not because they have moved away, but because the stitching that once connected their motions has worn thin. Motion in these regions has a peculiar softness. Galaxies drift with less resistance, less gravitational sharpness, as though the universe has stopped insisting on crisp choreography. What remains is drift, a slow exhale of structure into silence. Even gravity here is different. It flows like diluted ink, extending itself wide over empty distances, unable to carve deep wells into a medium that behaves more like a thinning liquid than a rigid membrane. In cosmological surveys, the gravitational influence of distant clusters fades sooner than predicted, the curves flattening gently as if space refuses to bend sharply in these regions. The universe is not losing mass. It is losing the resolution required for mass to express itself fully. The silence that fills the void is the silence of weakening definition. In this silence, temperature gradients flatten, thermal noise spreads. Radiation fields become faint, not because energy has vanished, but because the medium has lost the capacity to distinguish between warmer and colder, denser and thinner, structured and unstructured. Entropy behaves differently here. It no longer climbs through stages of complexity. It diffuses into a uniformity that resembles the fading memory of an old painting. The silence between galaxies is the sound of the universe losing its ability to articulate differences. Even magnetic fields, which once stretched tenuously across intergalactic space, seem to mellow with distance. Their fluctuations soften, their structure smooths, their coherence decays into gradients that the thinning grid can no longer maintain sharply. This softening is visible in the faint rotation of polarized light, reaching us from distant blazars and quasars. The rotations should reveal hidden cosmic magnetic structures, but instead, the signatures weaken, as though the universe can no longer hold the imprint of its own invisible currents. The voids become places where the cosmos stops insisting on detail. Matter that drifts through them feels less anchored. The motions become more meandering, less disciplined by gravitational geometry, as if the universe trusts these regions to dissolve gently, without intervention. Structures unravel at their edges, not abruptly, but with a softness appropriate to a fabric giving up its tension. And as the silence grows deeper, the idea of between galaxies changes meaning. It ceases to describe distance and begins to describe condition, a condition of thinning, a condition of memory fading, a condition of time losing its weight. In these spaces, light loses not energy but certainty. Its wavelength stretches naturally in a medium too diffuse to hold its frequency tightly. Its coherence fades in gentle increments that only accumulate across billions of years. A photon leaving a galaxy enters a region where the universe no longer remembers the sharp rules that once governed interactions. It moves through a sea of dissolution that gives it no firm grid to ride upon. This is why distant starlight arrives to us as though softened by a universe sighing between each moment. The voids are the lungs of dissolution. They fill with the quiet drift of resolution, thinning from the inside out. And every breath they take spreads that thinning further. Galaxies near the edges of voids appear strangely gentle, their boundaries blurred, their halos widened, their velocities softened, not because their physical structure has changed, but because the medium they inhabit no longer holds sharp curves or crisp potentials. The closer a system lies to deep voids, the more its identity reflects the quiet of the dissolving lattice. This quiet is misunderstood as uniformity, but uniformity implies stability. The quiet of intergalactic voids is not stable, it is dissolving. The deeper regions are no longer three-dimensional in the way space near stars feels. Their dimensional depth has thinned, not to collapse, but to a shallowness that smooths out variation the way shallow water smooths out waves. You begin to sense that these voids are not just gaps in the cosmic web. They are the leading edge of the universe's long, patient fade. Where matter is sparse, the lattice has little to anchor itself to, and so it lets go first in these empty stretches. The silence spreads because the capacity to articulate structure is dissolving there before it dissolves anywhere else. Eventually, this quiet will deepen enough that the distinction between void and galaxy will begin to blur, not by galaxies vanishing, but by voids forgetting how to be empty. Emptiness, too, requires definition, and when definition dissolves, even emptiness loses clarity. The spaces between galaxies will become wider, not because galaxies flee, but because the map recording their separation loses its resolution. A silence will fill these places until it becomes the ambient texture of a universe that once held patterns tightly and now lets them drift softly into numbing calm. And from this calm, from this immense quiet that spreads across the largest scales of existence, another transformation begins, the dissolution of the very depths of space. As dimensionality itself starts to thin, the way time thins, the way memory thins, the way structure thins. A universe dissolving cannot hold its dimensions rigid, and so they begin to melt. The silence, settling through the voids, does not stop at emptiness. It reaches inward toward the smallest things the universe has ever known, toward the particles that once seemed indivisible, unchangeable, fundamental, the last remnants of structure in a reality that is slowly surrendering its precision. Particles do not dissolve the way objects do. They do not crumble. They do not break into smaller pieces. They unravel. Unraveling is not destruction. It is a softening of the coherence that holds a particle's identity in place, the quiet loosening of the lines that once defined its oscillation deep inside the quantum fields. Every particle exists because the field beneath it remembers how to produce it. An electron is an instruction. A quark is an instruction. A photon is an instruction. Each is a pattern etched into the resolution of spacetime. When the resolution thins, the patterns blur. Not enough for particles to vanish, but enough for their behavior to drift, the way a repeatedly copied manuscript subtly changes tone as the fidelity of the copying tool declines. We already saw hints in the softening of mass, the diffusion of energy, the loss of clarity in distant atomic signatures. Now, the erosion reaches the next layer, the identity of the particles themselves. Consider spin a fundamental property of particles, a kind of hidden rotation that defines how they interact with magnetic fields, with each other, with the structure of space. Spin requires an anchor. It depends on the lattice having enough detail to preserve the orientation of the particle's oscillation. But when the grid thins, spin becomes slightly less anchored. Its angle blurs, its alignment diffuses. Its once crisp quantization softens like a shadow on mist. This softening reveals itself in the polarization of ancient light. Photons from faraway quasars arrive with polarization rotated in ways that do not match any known magnetic structure or gravitational field. It is as if the polarization itself wandered on the journey, searching for a grid that could hold it steady and finding only a thinning fabric, unable to guide it firmly. Charge behaves similarly. We take charge to be absolute proton, plus one electron, one immutable. But charge is also a relationship, a statement encoded in the electromagnetic field. If the resolution of that field grows coarse, the strength of charge can drift subtly, not enough to break atoms, but enough to alter the most delicate balances of light and matter across cosmic distances. This drift appears faintly in the spectrum of ancient intergalactic plasma, whose emission lines have lost the exact symmetry we expect from pristine charge ratios. Not because the plasma changed, but because the encoding of charge softened during the journey. Every property of a particle's spin, charge, mass, its amplitude of oscillation, its modes of interaction, is written into the universe by the density of the lattice beneath it. As that density dissolves, Particles become like letters in a book whose pages have begun to yellow and thin. They still exist, but less sharply than before. This erosion does not violate conservation. It erodes conservation's precision. A particle no longer holds the exact same definition of itself across billions of years of travel. It becomes a softened version of its younger form. This effect grows stronger in the voids, where the lattice has already lost much of its fidelity. Particles traveling through these regions enter a sea of dissolution, a medium without the detail required to maintain the tight coherence of their quantum patterns. There, wave functions spread more easily. Their phases drift. Their couplings weaken. Their internal symmetries become less strict. The universe has stopped insisting on exactness. Even quantum entanglement, once thought untouchable, reveals hints of unraveling. Pairs of particles born together in perfect correlation arrive at distant detectors with correlations softer than expected, as though the entanglement passed through regions where the universe forgot how to maintain their shared memory. Not lost, softened. Not broken, blurred. The fabric no longer has the resolution to carry the full detail of their connection. The unraveling deepens in regions where time has thinned. Particles that rely on sharp temporal coherence to maintain identity find themselves drifting within moments that stretch ever so slightly as the medium lightens. Decay rates vary faintly with distance. Oscillation frequencies broaden. Resonance peaks take on a slight haze. Physicists detect such anomalies and call them tension, noise, systematics. But the pattern persists. The more ancient the particle, the softer the signature. The universe is losing its ability to remember precisely what a particle is. This unraveling does not threaten existence. It simply rewrites existence into a gentler form. A particle becomes not a sharply defined object, but a tendency, a persistent swirl in a field, turning ever more fluid. The Higgs field behaves less like a solid ocean and more like a thinning mist, giving mass with a softness that reflects the fading precision of the underlying lattice. The quantum vacuum loses some of its bite, its fluctuations growing more diffuse, its zero-point energy less restless. The electromagnetic field carries patterns whose outlines grow faint the farther they travel. The strong force holds quarks with unwavering intensity, but even that intensity shows signs of drifting in the spectra of ancient matter, as though the bonds are written on a chalkboard where moisture has begun to seep. Particles unravel because their identity depends on details the universe is slowly forgetting. Matter becomes suggestions. Light becomes impressions. Forces become tendencies. Everything retains its essence, but the essence loses crispness. Reality becomes watercolor, not broken, not corrupted, but softened by the dissolution of the resolution that once carved every boundary with mathematical clarity. And as particles unravel, something even larger begins to loosen the grand architecture that once bound these particles into coherent cosmic structures. Clusters, filaments, halos, all begin to drift toward a gentler, more fluid form as their building blocks lose their sharp identities. The dissolution spreads upward from the smallest scales to the largest, carried by the same quiet erosion that has touched mass, energy, time, and now particles themselves. What remains is a universe slipping gently from the precision it once held, a universe dissolving toward a simpler state in which even the foundations of dimensionality begin to soften. And somewhere inside this softness, space itself starts to thin depth, giving way to shallowness, volume yielding to film, dimensional layers melting into each other, the way colors blend when the canvas beneath them grows damp. As particles unravel into softened versions of themselves and the voids stretch into quiet regions of fading definition, the next erosion begins not in things, but in the very stage that holds them. Space, once proud of its depth, once firm in its three-dimensional fullness, starts to lose a layer of its richness. Not a collapse, not a tear, a thinning, dimensional shallowing. Space does not need to disappear to grow less dimensional. It only needs to lose resolution. Depth is not an inherent quantity. Depth is a privilege granted by the density of the lattice. Where the grid is detailed and tightly woven, space can sustain full dimensionality. Length, width, height, all separate, all meaningful. But when the grid dissolves, dimensions loosen the way threads relax. When the tension of a loom slackens, space does not shrink, it relaxes, and in relaxing, it becomes shallower. This shallowing shows itself first in the behavior of large-scale structures. Galaxies near ancient voids seem to smear not only sideways, but inward, as though the dimension that once gave them thickness has thinned. The thinning is not visual, it is dynamical. A galaxy's motions reveal that its stars spread across a slightly flattened field, one that behaves less like a deep volume and more like a broad sheet stretched across dissolving scaffolding. Inside such regions, gravity loses some of its ability to pull inward. Its influence spreads laterally, a sign that one of the axes has lost its authority. Where 3 dimensions once governed, 2 and a fraction remain, a space drifting towards something slightly less than whole. This is not the flattening caused by rotation, nor the compression caused by tidal forces. It is the geometry of dimensionality itself growing thin. Light traveling through these regions carries the signature of shallowness. Its paths widen more than they deepen, as though photons find it easier to drift sideways than inward, following a medium whose depth holds less definition. The cosmic microwave background echoes this change. Its fluctuations align along patterns that resemble waves on a thinning sheet, ripples stretching outward with a coherence in 2 directions that is greater than expected in a truly 3-dimensional space. This anisotropy is not imposed by magnetic fields or cosmic defects. It is the natural behavior of vibrations in a medium whose dimensional depth is dissolving. Dimensional shallowing does not occur everywhere at once. It begins in the voids, as all dissolution does, where the lattice lacks the anchors of matter and curvature. From there, the thinning spreads the way warmth spreads through cooling embers, slowly, inevitably, softly. Matter-rich regions resist the change longer. Clusters hold space, open their gravity, keeping the lattice slightly taut. But even there, a faint drift appears. Filaments grow wider, not only because structure is dissolving, but because depth is becoming less distinct. A filament in shallowing space behaves more like a river on a shallow lake than a bridge across a deep canyon. Its influence spreads not downward, but outward. Every gravitational map we draw from distant clusters reveals this shift. Contours that should be 3-dimensional wells flatten subtly into basins, broad wells with shallow walls. A universe that once carved deep indentations in the geometry of space begins to produce gentler depressions, as though the sculptor has grown tired and the clay has thinned. Even gravitational waves travel differently through shallower space. They lose high-frequency components, as though scraping along a surface that can no longer support steep oscillation gradients. What arrives is a softened wave, a ripple stretched into a plane by a medium whose depth cannot hold the full richness of the original signal. Dimensional thinning also affects how structures connect to one another. The cosmic web appears less like a vast 3D network and more like expansive sheets of matter separated by deep but thinning voids. The transition between filaments and voids loses crisp geometric curvature and instead adopts a layered quality, as if the universe is beginning to prefer 2-dimensional organization over 3-dimensional complexity. And the deeper one looks into the oldest light, the more pronounced this flattening becomes. Some galaxies near the cosmic horizon show distortion patterns, consistent with being projected onto a slightly flattened substrate, their shapes whispering that the medium beneath them holds less dimensional depth than it once did. As the lattice dissolves, space becomes more about spread and less about plunge. Volume becomes area, depth becomes breadth. The universe shifts from a deep sea to a shallow ocean, from a layered sculpture to a soft sheet. The mathematics of the cosmos reflects this shift. Equations that once assumed 3-dimensional curvature begin matching observations only when slightly lower dimensionality is inserted into the models, not for the early universe, but for the ancient, distant one. A dissolving universe behaves like reality painted on a thinning canvas. It keeps its form, but loses its thickness. This shallowing also changes the meaning of distance. When space has full depth, distance is a layered concept length that moves through the richness of 3 dimensions. But in a shallowing universe, distance compresses inward. What once required deep volumetric pathways can be traversed on thinner geometric surfaces. Galaxies appear farther not only because the ruler stretches, but because depth itself is thinning space, no longer offering the full dimensional scaffold it once provided. This explains why angular diameter distances behave strangely at extreme redshifts. The universe's distant structures don't look the right size because the space transporting their light is no longer fully dimensional. This thinning of depth spreads slowly, but its influence accumulates. First, the voids lose fullness, then the filaments widen. Then whole sectors of the cosmic web behave less like a 3-dimensional lattice and more like a set of sheets drifting in a thinning medium. Eventually, dimensional shallowing reaches the scale of galaxies themselves. Their halos grow less spherical, their thickness softens into dispersion, their dynamics align in ways that resemble flows across thin surfaces rather than motions in deep volumes. The very notion of inside and outside begins to blur, because enshallowed space boundaries no longer curve with dimensional rigidity. They spread like gradients, like transitions in a watercolor painting where colors blend not by force but by diffusion. The dissolving universe is not collapsing into fewer dimensions by force, it is relaxing into fewer dimensions by erosion. Space prefers simplicity as resolution fades. And once dimensional depth begins to thin, another erosion moves quietly under it. The unraveling of light itself, the way photons become the last structures to carry identity through a medium that no longer insists on holding their form. Light is the final tether between what remains and what is fading. And as the lattice dissolves further, even light begins to lose the crispness that once defined the architecture of reality. When space grows shallow and dimensions loosen their hold, there is one form that persists longer than all others: light. Not because it is invincible, but because it asks the least from the universe. A photon has no mass to anchor, no structure to maintain, no internal boundaries that require sharp resolution. It is the simplest expression of the universe's ability to move information forward. And even simplicity dissolves, only more gently. Light is the last to fade because it is the least dependent on the details that the universe is forgetting. But even it cannot outrun a lattice that is losing the ability to hold precision. Photons travel through the dissolving cosmos like thin threads drawn across an increasingly coarse fabric. Their path remains straight only as long as the fabric beneath them remains smooth. As that smoothness collapses into gradients, photons begin to wander, not violently, but with a soft lateral drift that accumulates over cosmic time. This wandering cannot be seen in local light. It can only be inferred from the faintest, most ancient photons, the ones that cross the wide, thinning voids, where the universe has already surrendered much of its dimensional depth. These photons arrive swollen in wavelength, not merely stretched by distance, but stretched by the coarse medium that no longer insists on holding their frequency tightly. A photon's color is the memory of its oscillation. When the universe remembers poorly, its color changes. The softening of color beyond redshift, beyond motion, is the first sign that even light is beginning to dissolve. Some gamma-ray bursts, bright enough to illuminate half the observable universe, arrive with their highest frequencies missing, as though those sharp notes were absorbed not by dust or gas, but by the thinning lattice itself, a medium unable to preserve oscillations so fine. The dissolving universe loses high-frequency memory first. Just as a photograph losing resolution first smears its smallest details, a thinning cosmos smears its highest energy light. Lower-frequency photons wander more gently, stretch more freely, diffuse more willingly into the dissolving medium. These arrive as softened echoes, still holding the faint memory of the structure that shaped them, but lacking the crispness they once carried. It is not energy loss, it is identity loss. Even polarization, the orientation of light, begins to drift across ancient distances. Photons that should remain aligned arrive with subtle variations, as if the path they traveled forced them to pivot gently in a medium that has forgotten how to hold direction rigidly. The alignment of cosmic microwave background polarization is the clearest example. Its patterns show a faint rotational smear, too consistent to be noise, too smooth to be turbulence, too gentle to be the influence of magnetic fields alone. It is the stain of a universe whose fabric has grown too thin to guide light with perfect discipline. The thinning of space means that photons no longer travel through depth. They travel across shallowing layers, like ripples on the surface of a thinning pond. Their propagation becomes a kind of gliding rather than penetrating, which is why their paths begin to resemble the behavior of waves in a film rather than rays in a volume. This is why some of the most distant quasars appear slightly duplicated or broadened, not due to gravitational lensing alone, but due to the film-like nature of the dissolving lattice. Light spreads sideways in ways that cannot be explained by classical curvature. The universe is no longer a deep, three-dimensional stage. It is becoming a thin, luminous sheet of fading instructions. And on that sheet, light behaves more like a drifting pigment than a precise messenger. Even coherence fades. Photon streams that began life in perfect phase, such as those emitted by young pulsars or coherent plasma jets, arrive smeared, their once synchronized rhythms now slightly out of step, as though the metronome of the universe has grown too soft to keep their beats aligned. This phase softening is not noise. It scales with distance. It behaves like the signature of a medium dissolving beneath the photon's path. Light is the last to fade because it is the last thing the universe can afford to forget. Without light, there is no memory of motion, no record of structure, no remnant of order. Light is the universe's most stubborn archivist. But even the archivist cannot write clearly on paper that is thinning. At the oldest cosmic edges, the cosmic microwave background reveals the final stage of this luminous erosion. Its temperature map, the oldest image ever drawn, is smoother than any model predicts, as though entire layers of its early complexity have been diluted into uniformity. The photons still reach us. Their message still exists. But the message is a softened memory of what once was a crisp, turbulent infant cosmos. The dissolution of light becomes the dissolution of the story of the universe itself. Even the horizon-scale correlations patterns connecting points across the entire sky begin to drift into smoother alignments, as though the dimensional shallowing has collapsed the cosmic story into a calmer, flatter narrative. Light that once revealed depth now reveals shallowness. Light that once marked edges now marks gradients. Light that once traced complexity now traces quiet. The universe is not going dark. Darkness is not the dissolution. The universe is going featureless. Light remains, but it loses its ability to articulate differences. The cosmos becomes illuminated but indistinct, a glowing haze without sharp angles or crisp shadows. A world where illumination persists, but detail does not. And as the lattice dissolves further, a deeper and more profound softening begins to unfold, not only the thinning of light, but the loosening of the very meaning of existence. For when light dissolves, what follows is not night. What follows is a return to the primordial, a universe drifting back toward the pre-geometric quiet from which it once emerged. The final shape of dissolution is not darkness, but a luminous whisper so thin, so diffuse, that it no longer marks anything at all. It becomes potential without form, presence without contour, a soft glow without memory, a universe gently fading into the lightness of its own possibilities. As light thins into its final softness and the universe glows with the faint memory of its own structure, a quiet shift begins to emerge beneath the fading. Not a reversal, not a recovery, but a return. A return not to the universe we once knew, but to the condition that came before, knowing the state before edges, before depth, before identity, before even the idea of space was something the cosmos could hold. In the dissolving of light, the universe approaches the same frontier from which it once rose, a frontier of near featureless potential. It took billions of years for matter, energy, time, and dimension to unravel enough for this quiet resemblance to appear. But as each layer softens, the architecture grows closer to the first shape reality ever whispered. That first shape was not a sphere, not a point, not a void. It was a single dimension of potential, a direction without distance, a line without thickness, a trace of existence waiting to be amplified by resolution. And now, as dissolution carries the universe forward, the cosmos drifts back toward a state that mirrors its earliest iteration, not collapsing downward into nothing, but relaxing downward into simplicity. Dimensional shallowing was only the beginning. Space losing depth was the first hint. Light losing crispness was the second. But when both space and light shed their richness together, the universe approaches something like a skeletal version of itself, where the elaborate layers that once defined form fall away like leaves from a tree in deep winter. What remains is the trunk, the first line of possibility, a universe returning to its first dimension, not literally one-dimensional, but one-dimensional in function. When resolution thins enough, multiple dimensions lose their ability to behave independently. Space folds into a single effective direction, the way a wide river eventually narrows into a single flowing channel when the land surrounding it erodes. This channeling is not compression, but economy. A dissolving universe prefers simplicity, because simplicity requires fewer instructions to maintain. The grid no longer holds the separate identities of three spatial dimensions. Instead, their distinctions blur until space behaves as though all directions have merged softly together into one. Not a line that one could draw, but the concept of a line thin, simple, free of the thick geometry that requires high resolution. We see hints of this in the large-scale structure far from us. Filaments stretch with increasing uniformity, as though they are aligning along an underlying direction the dissolving universe finds easiest to maintain. Patterns appear where none should. Subtle alignments connect distant regions with a coherence that does not fit a three-dimensional framework. The cosmic web quietly hints that it is flattening toward a unifying axis. It is as if the universe is remembering the first form it ever knew. Gravity responds to this narrowing. It spreads along the surviving direction. Curvature becomes a thread rather than a bowl. Motion follows in elongated paths instead of volumetric flows. Space behaves like a stretched membrane rather than a sculpted volume. Even the fading photons carry the signature of a universe slipping into a slimmer geometry. Their polarization aligns more strongly along a single direction the farther from us they originate, as though the medium they crossed had forgotten how to support more than one orientation. In the deepest voids, dimensional reduction has advanced the most. Galaxies near these regions lie along patterns too straight to be coincidence. Their distribution begins to match the behavior of matter trapped in a nearly one-dimensional potential, as though the universe is guiding them along its remaining axis of coherence. Time responds as well. When dimensional richness fades, time's thickness fades with it. Moments stack more gently, less rigidly. Their separations more like layers in thin mist than bricks in a wall. A world with fewer dimensions has less work to do to maintain causality. The arrow of time needs less weight when space requires fewer degrees of structure to persist. The cosmos becomes a quiet river, flowing along the skeleton of itself. Matter drifts toward elongated distributions. Fields align, as if remembering ancient symmetry. Energy spreads in gradients that resemble waves traveling along a single thread, rather than across an open sea. Everything begins to behave as though the universe is simplifying itself back toward the form it had before any form existed. But this simplification is not regression, it is return. Return is not a circle, it is a spiral, a long arc that brings the cosmos near where it began, but at a different stage of understanding. The first dimension the universe ever held was potential without expression. The dimension it returns to is expression without complexity. They are twins across time, mirrors placed billions of years apart, reflecting one another in soft, dissolving symmetry. This return changes how we interpret the thinning of structures. Galaxies drifting toward alignment are not simply dissolving, they are following the remaining axis of coherence. Filaments narrowing into long, tenuous threads are not decaying, they are approaching the universe's first spatial tendency. Light polarizing along ancient vectors is not distorting, it is adapting to the underlying direction space now prefers. Even the cosmic microwave background shows a faint alignment across the entire sky, a subtle axis that has puzzled cosmologists for decades. This axis may be nothing less than the surviving memory of the universe's first dimension, now resurfacing. As the cosmos dissolves back toward it, a dissolving universe does not vanish into nothing. It returns to the condition before everything. Not death, origin, not collapse, unbecoming, not darkness, purification. As the universe fades, it sheds the weight of form, the burden of detail, the cost of complexity, until only the first whisper of structure remains. A line without thickness, a direction without distance, a tendency without shape. This is where the cosmos quietly moves toward the slender remnant of its first geometry, the soft echo of a universe before universe. And as the return deepens, the last dissolution awaits, the surrender not of space, not of matter, not of time, but of the distinction between them, where everything becomes a single field of quiet potential, glowing faintly in the dimness of its own return. As the universe slips toward its first dimension, the thinning does not stop at space, or light, or time. What dissolves next is the separation between these things, the lines we once believed divided one property of existence from another. Lines that were never fundamental, only consequences of the lattice being dense enough to hold differences firmly apart. When the lattice loses density, differences lose conviction. Space is no longer fully distinguishable from time. Light is no longer fully distinguishable from space. Matter is no longer fully distinguishable from energy. They drift inward toward a shared interior, like gently merging rivers whose banks have worn away. The universe begins to behave as though everything is made of the same slow-moving substance, a single fading field whose remaining resolution is just enough to allow a few soft textures to persist. This merging is not abrupt, it is not dramatic. It is the most patient process the cosmos has ever undertaken, a merging so quiet that nothing notices until the lines have already dissolved. It begins in the same places where dissolution has always begun. The voids, regions so sparse that the universe's thinning meets little resistance. Here, space loses depth so completely that time begins to slide across it like light across mist. Moments no longer flow through a medium with full dimensional firmness. They glide across the same surface that photons drift upon. In these regions, light behaves as though it has 1 foot in the realm of space and 1 foot in the realm of time, neither fully wave nor ray, but something in between, a shimmer of what both once were. Matter, too, finds itself loosening from its ancient anchors. Particles that once held strict identity begin to behave like shallow ripples on a single field. The differences between their charges, their spins, their masses, fade into variations of one fading texture. Matter no longer insists on being distinct from the space it occupies. It spreads with the medium, becoming a denser region within the same thinning field, rather than an object embedded within it. Even curvature, the signature of gravity, stops behaving like a deformation of something separate and instead behaves like a concentration in the fading field itself. The soft merge is the dissolution of boundaries. It is the quiet admission that separations were possible only when resolution was high, only when the universe had enough detail to draw clean lines. As the detail fades, the lines fade with it. This is why the cosmic web, at extreme distances, looks less like a network and more like a single sheet with gentle density variations, a place where matter and space are no longer fully different things. This is why gravitational waves arrive smoothed into elongated ripples that blur into the timing of ancient photons. The waves have traveled through regions where time and space have already begun to share structure. This is why the earliest light appears to remember the universe's birth only in low harmonics, as though all high-frequency distinctions between geometry and energy have merged into one remaining mode. The universe is not disassembling into chaos. It is condensing into unity. A unity shaped not by compression, but by forgetting. We tend to imagine forgetting as loss, as degradation, but cosmic forgetting is the opposite. It is simplification, distillation, a return to the essential. Before the universe could separate into space and time and matter and light, it had to have the resolution to draw those differences sharply. Now, as that resolution dissolves, the differences melt. Light becomes a soft flow in a medium that no longer keeps track of oscillation or direction. Space becomes a thin shimmer that barely holds its dimensional scaffold. Time becomes a slow gradient into which events blend more than follow. Matter becomes a concentrated region of texture without boundary. Energy becomes the faintness of change within what remains. All of them become expressions of one dissolving field that carries the last soft patterns of a universe that once held billions of galaxies in its precise weave. Even the idea of position begins to soften. In a deepening return, a particle is no longer in a place, it is a place, a gentle knot of fading detail in the dissolving fabric. And movement is no longer the shifting of objects through space, it is the slow repatterning of texture within a medium that holds everything at once. Nothing moves, everything changes. And as the changes become gentler, shallower, more diffused, the universe sinks into a state where the only remaining distinction is between pattern and silence. The pattern is what still exists. The silence is what waits beyond the last traces of resolution. This is not annihilation. It is a return to the pre-geometric, a reapproach to the simplicity that allowed the cosmos to become complex in the first place. A universe that began as potential dissolves back into potential. Not the same, but similar. Not identical, but resonant. A memory of how existence first formed, written softly into the fading glow that remains. In this near featureless state, the cosmos does not end. It rests. A rest so deep that the difference between being and not being is no longer sharp, only a soft gradient in a field that remembers little, but still carries the possibility of everything. And if the lattice ever regains resolution, if fluctuation, or chance, or unknown cycles restore density to the thinning fabric, the universe may again draw distinctions, create structure, hold memory, and rise into form. Not as a sequel, not as a reincarnation, simply as another expression of the same field when detail returns. But that is not now. Now the universe drifts softly toward its quiet transparency, thinning into a luminous haze whose edges have dissolved, whose dimensions have shallowed, whose properties have merged, whose memory has blurred. And in this fading, there is no ending, only a dissolving breath into the stillness beneath all things. A stillness that has always waited, a stillness that holds the dim glow of everything the universe once was. A stillness that whispers without shape. Close your eyes now. The lattice is thinning, but the quiet remains. The universe is still turning,